Yeah, testing, testing. Oh, but
There's going to be a bounce, yeah.
uh
Okay. Sounds like there's going to be an echo though.
Maybe we can turn off the speaker here. Maybe.
Can you hear me now?
yes, we can.
Okay, that's good. I hear you through my laptop, so it might be a little bit weird. All right, so the point of WebAssembly is an efficient low-level bytecode. It's close to native performance. It has an extremely rigorous specification. Many languages and toolchains are already targeting it. It was born on the web, so if you know anything about how German things are named, they're named for where they came from. So the name WebAssembly is kind of like that. It's like named from the web, although it runs in many other places. It is a candidate for universal bytecode, and I am going to give a funny little anecdote thing. So I don't know if we can get rid of some of this stuff. I don't like that. Oh,
Use the room mic instead of the laptop.
Test.
No, the bars on.
Yeah, correct.
To be honest, I think the setup that we have now is fine because they can hear me through the laptop.
They can hear you now.
Yeah,
That means, do you still need to do the
I
setting?
think it's fine. I think we're just gonna go with this.
You turn that off because there's an extra.
Yeah.
Yes. You be okay now?
Yeah, you gotta mute that. Mute that.
Yeah.
Thank you.
Oh, okay.
Okay, I think we're gonna go with this. All right, so this is kind of a rhyme. I came up with this with some help of the AIs that can do words well. Why do we constantly go from having something simple, which is a lamp, which has got a very simple control system like toggle on and off, into suddenly it can run a script language? And the answer is that parable of the lamputer is how we get here. So back at the start, there was a lamp. Then we made toggle inspect with a stamp. This makes sense from a hardware point of view, right? Like you start with something very simple, a very simple interface. And the point is that the hardware people actually got the minimum thing. And you have to write a specification, right? So you have to pick a language to write the specification in. In this case, it's German. So any of you know German? I will read it. Fordert die Lampe auf, den Zustand auf 1 zu ändern, wenn der aktuelle Zustand aus ist und umgekehrt. Gib den aktuellen Zustand zurück. So if you don't speak German, there's something really important in the details of the specification, which you might be hidden in there, which is that it returns the current state. And with that, you can make something, and we'll see. But toggle alone meant 2 calls to check because client insisted on off with spec. So maybe we don't want a lamp where you have to toggle it, but maybe you want to be able to turn it on and off and be certain that you get the final state. And you have to write a program to do that because now it's a programmable thing. And so the specification of that also has to come in the specification language, right? So you can use 2 calls, but there's also something now that's hiding in there. And really the spec people are telling you that you need to do this, that you have to do it your own. Of course, this is suboptimal from a latency perspective because you've got 2 calls. You've also got potential race conditions because you have 2 toggles that could come in and maybe you don't get the state that you want. So the next thing that happens, soon perf pressure they could not resist and set on off was next on the list. So they decided that they should probably add something that also needs a specification. And so we get our latency improvements at the cost of adding some functionality and also needing to write some specification language. And so there's also something hidden here for you, for those of you who might understand German, is that it can fail. So there's something in the spec, which is a hidden little detail, which you only know the spec language do you actually get. So then came new features all in a flurry. All we could do is spec in a hurry. So suddenly they decided, oh, it is possible to add things. So why don't we add as many things as necessary? And we are writing lots of specs now. So we're adding features. It tells time. It's not just a lamp. It's a lamp clock, a lamp clock. And other people want other things. So more features are showing up. And those are going to now need specifications too. There are features that you can advertise, but they each are going to require you to write some of that spec language. And so you can kind of see where this is going. It's not just a clock anymore. It's basically a file system. And you end up with the gotchas in the specification language. Some things are underspecified. Some things may be deprecated. Some things might have a really bad downside. Soon, behold, a language oh neat. Next thing you know, it's Turing complete. So this is how you end up with the lamputer, right? You start adding commands and commands and commands, and then suddenly you cross the threshold and it can do anything. And so you have this like bespoke language, which has evolved from the things that you've added to your computer. And since it's Turing complete, that means that you might want to program it in a language that you're already using, JavaScript or Java or Python, and you write a compiler. We thought we were clever, but it turned out a mess. WASM's clean core would have saved us the stress. The point being that I think if we're going to be developing new kinds of computers that are programmable, we should start with something, and maybe we could just use a subset. So that's kind of where we're headed, right? So the lessons are basically that all the programmability is leading towards Turing completeness, and the intermediate steps are basically the things that are causing the problems. There's a lot of weird VMs out there. You say we should probably think about using WASM. That's why I'm here. talk to you a little bit about WebAssembly. All the things that I mentioned here, there's lots of papers behind this, so it's like an accelerating research field. All of you are no doubt researchers, so you're interested in that. Okay, now we're going to break down WebAssembly modules a little bit. Has anybody not seen a WebAssembly module before? Okay, so this is enough background so that it will make sense. All the code comes in packages called modules, and they're binary. There's a text format, but the point is that it's a very efficient binary format. There's a lot of different sections in the binary: types, imports, exports, function definitions, and it's got bytecode in there. So WebAssembly represents a type stack machine. So there's a static type system and there's structured control flow. One of the nice isolation properties about WebAssembly is that a module only has access to what's explicitly been given to it, what it's requested, and what it's been linked to in the host environment. And so that also is a good and bad thing in the sense that there's no system interface. There are some interfaces that you can get to on the web through JavaScript, but in other areas, maybe there's not a system interface. So there's a higher level problem that how do you make something that you can actually program the outside world? So the point is that it's a high performance sandbox. Okay, so we're going to get deep into WebAssembly. So I thought we'd get an overview of the instruction set. So there's a lot of instructions. There's over 540 instructions, but I've helpfully classified them into categories that I think make sense. First of all, there's a huge chunk of instructions that are vector instructions. There's basically 128-bit vectors. You can do lots of parallel adds and horizontal adds and things like that. There's things that do integer and floating point arithmetic. A lot of those things, basically all pure operations. And there's stuff to deal with storage. And actually the sort of core complicated things that deal with functions and control flow and stuff like that, it's actually a really small subset. So it basically breaks down like this. There's a few that are kind of like administrative instructions. So there's an explicit no-op instruction, which doesn't do anything. Then there are instructions that basically represent a control flow block and delimit a block and also a loop, and also delimit a block for exception handling. There are instructions that do actual control flow. So there's an unreachable instruction. So for example, if you have a safety check you insert into your code, you might have an if and then an unreachable for the case where it should fail. But control flow is done with if else and all these BR variants here. So you can branch on an I32. You can also do a multi-way branch like a switch. You can also do null checks and things like that. Those are mostly in the WASM-GC extension. And then you can also branch and cast at the same time. And these last few at the end, these are for doing lightweight stack switching. So having a lightweight and also algebraic effects. I'm not going to talk a lot about that. But once this set is complete, that's basically all you need to be able to express all the local control flow. And then to call functions, there are 3 byte codes to call functions. So calling a function directly, that's call. And then an indirect call is done through a table. And so that basically takes a runtime value that represents the function. And there's also one which takes a typed first-class function reference called ref. And then there's tail call versions of those. Those are the same operation, except that they will remove the calling frame. And so you can do like a proper tail call in your functional language. Okay. For dealing with local data, basically you've got instructions to deal with the operand stack. So there's a drop. It's basically if there's a value on the top of the stack, just drop it. You can select between a number of different values and without doing control flow, that's select. And then to access the local variables, local get, set, and t, and then there's constants. So that's basically all you need to know about like what the set of like the core things are. So without thinking about integers or floating point or vectors or anything like that, that's the sort of generic things at the base of WebAssembly. Okay, and I mentioned unmanaged storage. And so what I mean by this is that there's not a garbage collector underneath this. So this is like the memory, which is a big kind of byte array of like storage, very similar to a hardware memory. Tables, which are basically arrays, which are not first class, and global variables. Okay, and since 2024, the WebAssembly GC extension or proposal has become part of the standard. This actually does introduce managed storage. So there are fixed size structs. We'll see that maybe in a bit, but basically these are like a low-level object system. So it doesn't have methods, but they're like records. And so those are allocated on a heap that's managed by the VM. And so you can do the normal width and depth subtyping that allows you to build the object model of your language. So you can implement Java object model, you can implement Scala's object model or functional records and so on. You can also have arrays, those are dynamically sized and indexed, and then the cast between different types. So it's basically a very low level system where you can map multiple different languages down into it. Okay, so that gives you the storage abstractions of WebAssembly. So you've got unmanaged storage, it's kind of like byte-oriented and primitive-oriented, and then you've got managed, which is all on the heap. And then there's a bunch of integer arithmetic, all the typical things. Yeah. So the question is, how do you allocate memory? So if you're using unmanaged storage, a WebAssembly memory is effectively a giant byte array, which could be kilobytes or megabytes or even gigabytes in size. And so your memory allocator would be implemented in WebAssembly and it could carve up that memory.
Okay, so you need to implement a memory allocator that has access to this, like who specifies how big that array is?
So the module specifies the size of its memory. And it will give an initial size, and the size is in terms of pages. Right now, the page is 64 kilobytes, and you can specify a maximum size, and you can grow a memory. And so growing a memory will succeed up to, modular resource exhaustion will succeed up to the maximum of a memory. And the reason why we chose 64 kilobytes is so that you can implement a WebAssembly memory using the hardware page protection mechanism, virtual memory system. So when you go out of bounds of memory, you don't actually have to have a bounds check on every memory access. That can be done by the CPU. Does that make sense?
Yep.
Are there other questions about that? About any of the WebAssembly stuff? This is a very high level picture of it. Okay, and then we got IEEE 754 floats. That took quite a bit of wrangling to actually agree that we should do IEEE 754, but we got there. And so this is like, you can just take that spec and look at effectively any one of the instructions does what the spec would specify. Okay, so then there's this huge vector unit and growing. So we basically took the intersection of all the 128-bit vector operations on the common CPUs. So those are things like if you take 128 bits and view it as 4 32-bit floating point numbers and then want to do a parallel add, so like a F32 by 4 add, there's an instruction for that. So this is very enumerative in just like finding all the things in the matrix of this operation over this many things. Does that exist in the CPU? Yeah, it goes in. So there's about 250 vector instructions. And there's a lot of weird instructions, like what if you want to take some of the lanes and move them like this, or move them like that, or move them like that? And all those are a little bit different in hardware. So we had to kind of find the intersection of those. So that's kind of how SIMD came about. But you can basically get these and they effectively map one-to-one onto what an Intel CPU would give you and an ARM CPU would give you modulo a few things. So it's a pretty big speed up for certain applications. All right, so we got all the arithmetic we could ever want. So you can kind of think of WebAssembly in a nutshell as being this, the instruction set architecture and the data model. So you've got all the instructions that kind of fall into those big groups. And then the data model is that you have the big memory or multiple memories to store data, tables, which are things can store references. You've got global variables, the stacks for running your actual functions, and then you've got this GC managed heap. Does that make sense? Any questions about that? Okay, so you guys are
Hi, I was just wondering about this wrangling thing you mentioned.
Yeah, go ahead.
So why did they need to have wrangling to get to IEEE? Is there some special problem?
So the question for those in the room who didn't hear is, why was there wrangling to get to IEEE 754? It is a bit of a tangent, but as it turns out, almost most early GPUs did not actually implement all of IEEE 754. For example, the subnormal numbers. And Intel CPUs have a slowdown when you run into the subnormal range because it becomes complicated. That's all part of IEEE 754. That is very useful for numerical stability for certain algorithms. But to save transistors, you can typically flip a mode where all subnormal numbers go to 0. And so that will be faster in CPUs and GPUs and early vector units like an ARM had this, but it's not part of the spec. So this flush to zero mode is not part of the spec. And so we actually had a long argument about whether we should have a flush to zero mode, whether it should be undefined, what exactly should it do. And I think where we ended up with is basically the spec is a spec. We're not going to wander off into having weird performance features that random hardware implements. And
Okay.
that's how it took a wrangling. Does that answer your question?
Yep, thanks.
Okay. Okay, so I'm curious about what people in the room are interested in. So we had planned on going through mostly dynamic analysis stuff. I'm going to talk a little bit about Wizards architecture, which is the research engine that we developed. And we're probably going to live code some of that. Elizabeth's going to talk about WAMP, but there's a whole selection of things out there. So in terms of the spec itself, there's been mechanized specifications before the actual spec was turned into something that we could mechanize. So those are like WASM-Ref Cock and WASM-Ref Isabel. Now the specification is actually officially going to be written and is indeed in WASM 3.0 written in SpecTech, which is a DSL for writing the spec. So how many people are interested in SpecTech? There are at least 3 people. So I will give you an advertisement for the WebAssembly workshop. The very first session on Thursday, we're going to talk about SpecTech. And Andreas is going to talk about it. And since he's the primary guy behind it, I think he's going to do a better job than I could. How many people are interested in verification? Okay, so Iris WASM is one of the big tools in that space. Also not an expert in that. But this is like, if you want to verify properties about WASM programs, this is a formal framework for doing that. How many people are interested in benchmarking? A couple of people. So benchmarking in the WASM space is about as hard as benchmarking in any other space, except it's even harder because there are more engines. It's more diverse. So there are at least 8 to 10 engines of interest out there that you might want to measure depending on what you're doing. One of the tools that we built over the summer, I had a master's student over the summer built this tool called WASure, which is basically a manager for like the dimensions. Like if you think about all the different benchmark suites that you could possibly run, all the different engines you might want to run, different configurations of the engines, WASure is basically this Python program that manages all of that for you and can do like, you can run various things in different configurations. We haven't done we're writing a paper about this right now, but we haven't done a lot of advertising about that, but that's something that we've used to make it a bit easier to manage all of that space. So how many people are interested in fuzzing? A few people. So I've seen several papers on fuzzing, and there's a bunch of tools out there. I think probably the best developed one is the one which is in, I think it's called WASM Fuzzer, but there's a whole bunch of different things that you can do in this space. And I haven't personally used these tools. I've run the fuzzer on Wizard a little bit. I think I've run WASM Fuzzer on Wizard at some point, but it is also something that's like an active part of research too. Okay, so I have used the test case reducers though, because as it turns out, there are bugs in my VM, and when it crashes, I would like to get the bugs to be smaller reproducers. So Binary N, which is a tool set which has lots of different things in it, has WASM reduce inside. And so I've used that to some effect on a lot of test cases that have come along. As well as an optimizer too. So like Binary N is basically this big, and is a big collection of tools that has all kinds of things. How many people are interested in record and replay? Maybe a little bit. So we've done some work in that space too. So there's a tool called WASM R3. And so that is basically record and replay for WASM programs. So as I mentioned, WASM it can run on the web, it can run in other system domains. But if you take a program from the web and you want to run it on an engine that does not fit in a web page, what do? And so WASM R3, the idea is that you instrument the WASM program and it records all the interactions that it has with the outside world automatically. And so it does that by basically having its own internal copy of memory and then a copy of memory that is shared with the outside world. And the copy that's shared with the outside world can be modified by the outside world, but the internal copy cannot be. And so anytime the program reads from memory, it reads from both memories and then compares them. And then if the outside world has changed memory, it will be able to detect a difference. And so you can do this so that at the boundaries, you notice that, for example, a host function has changed something. Yeah.
Talk a little bit more about WASM. I'm not sure I got that.
So WASM opt is a WASM to WASM optimizer. It's a static optimizer. You give it your binary and you can give it lots of different flags and it will go and do, for example, you can do closed world assumption. So you can say, assume that this thing does not link to another WASM program that somehow calls into it in a way that we don't understand and optimize it fully. So that mostly doesn't matter that much for WASM prior to WASM GC, but with WASM GC, there are things that could be different depending on how you assume another program might use WASM GC types because of WASM GC type canonicalization. But the point is basically you can flip tons of flags. For example, you can assume no memory access goes out of bounds, and therefore some reorderings are more possible than they would be, according to strict WASM semantics. You can also say, assume that, for example, like NANDs don't occur, or like maybe we don't care about like, I don't know, maybe we don't care about the exact like commutativity of floating point operations. So there's like lots of configuration options. So this can do the optimizations that your static compiler wouldn't. So if you're targeting WASM with a language where you haven't built a big optimizer for, you can reuse that as like a part of your tool chain. So there are a lot of languages that actually do that. So if you build Scala, then the Scala optimizer, for example, basically farms it out to WASM opt. Yeah. Yeah, you can use it as at the end. And so for the most part, I think the defaults are that it won't change your program's behavior. That's kind of the nice part of an optimizer. But if you start flipping those flags, it can subtly change your program behavior. Okay, there are a lot of different engines out there for WASM. So obviously all the web browsers have their own JavaScript engine, and they all have a WASM engine inside their JavaScript engine. So V8 has one, SpiderMonkey has one, and JSC. Those share zero code. They're all completely independent implementations, which means that they hopefully all implement the spec correctly and they don't have any differences. I think for the most part, those things are just bugs. But each of them also have their own command line tools. So like you can build V8 so it has its own like REPL. And so Node is actually like a sort of super duper REPL around V8. The V8 has D8, which is its own sort of lightweight REPL. So you can run WASM in a command line way just using D8. And you can also, these web engines, so you can do the same for SpiderMonkey and JavaScript core. You can also build their command line versions, and then you can run things. So I think Bun uses JSC underneath. And so you can also do the similar kind of thing. Bun can run V8 WASM code. So for other standalone engines, so none of these actually run on the web. So WASM time, this one is written in Rust. This is probably one of the most prominent ones. This is used in a lot of cloud and edge applications. WAMR is used more in embedded applications. WASMer is kind of also edge, is same with WASM edge. And WASM 3 is an interpreter-only implementation. That's mostly for embedded systems. In the research space, there's been Wizard, which of course I work on. There's also a few research papers. One of them came up with, for example, like copy and patch compilation, applying that to WASM. That tool is called WASM Now. So you can try out these different things. There's a lot of different instrumentation frameworks too for WASM. So Wasabi is one. So this is JavaScript based. It's basically, it injects calls into your WASM code that go out to JavaScript. So you don't have to necessarily run it in the web. You could, for example, run it in D8 or any of these other engines and then implement your instrumentation in JavaScript. Wasabi is known to be a little bit slow because you have this like JavaScript call for every time you do instrumentation. Wastrumentation is a new paper that came out recently, I think in eCoop this year, and this is Rust-based, and so this uses Rust macros and bytecode rewriting. So you can write some instrumentation in Rust and then get it injected, and then you basically get a WASM program out that will call into your instrumentation. Elizabeth's going to talk about WAM, and that is all a DSL that we've developed. Okay, there are questions about the overview of those. We're gonna go and dive deep into Wizard. So I'm going to give some slides about what Wizard is about. Any questions before I do that, though? So when I was in grad school, JIKES RVM was all the rage. I thought it was really cool. People were building Java, and Chex RVM was a Java and Java VM, and it really got a lot of traction. There was more than 188 publications. A lot of people got their PhDs, and it was really there that made it Java VM research accessible. I kind of want to do the same thing with WebAssembly research. And the point is basically, you can't really use a production engine to do research unless you're already really good at production engines. So I worked on V8 for almost 7 years. V8 is a complicated beast. And even with my own guidance, students are not able to get into the code base to do research with any of these production engines. It's tough. So the point is that it makes it easier for students who are just learning. They don't know how VMs work. They should have an example where they can look at something simpler. Another thing is that production engines can't really afford to be extremely flexible, so they can't really be designed to serve the master of research at the same time they're trying to be a product. So they really need to be fast. So having a research VM out there actually takes pressure off of production VMs so they can focus on their product needs. And also, WebAssembly is still evolving, so we want to steer the language evolution by being able to explore language features. So Wizard is all about observability. We're going to see observability today. Should be approachable. It should have competitive performance. It's not going to be as fast as a production engine because it doesn't have all the things of a production engine. If we compare that to V8, it's basically got one priority, which is the product should be fast. And way down the list is somewhere basically engineering concerns, like the evolution of the engine itself and the people working on it being able to manage the complexity. And so those other priorities are way down here. Yeah. It needs to be reasonably close. So if I would put a number on it, baseline compiler is basically a single pass compiler versus an optimizer compiler. The gap is about 3x. So if a production engine is here in performance, get to within 1/3 of it. And the point is that it should be transferable in the sense that if you get a performance result, you should be able to think of what it will be on the production engine without and reduce that gap. Sound like there's some question on the chat or on the Zoom. Nope. Okay, so one of the things that Wizard has is an interpreter. And so this interpreter is really driven towards this observability use case. And it's also about cold code, startup, and memory consumption, and it's about instrumentation. I'll give a little bit about it. So I wrote a whole paper about this in Uppsala if you're curious about the details. But basically, on the left, we've got WebAssembly bytecode. On the right, we've got some runtime representation of what's going on. So there's an operand stack and there's a call stack. So the operand stack we call the value stack because it includes locals. And there's this additional data structure that the interpreter needs. So Wizard's unique in that it runs the WebAssembly bytecode in place, meaning it doesn't rewrite the bytecode into another format. And so that's important because you can tell the user the bytecode offsets, you can allow them to insert instrumentation, any trap or anything like that. So everything in the VM is driven towards the original bytecode as the source of truth. And the side table is basically how we get there. There are other interpreters. So WASM 3 has an interpreter. JSC actually has an interpreter, and they both do rewriting inside. Because of that, they don't have as many tools for doing instrumentation. But this is the trick that you need to get to being able to do the instrumentation. And performance results aren't that important. But it's also faster for startup because you don't actually have to rewrite the bytecode. Okay, but an interpreter is an interpreter. Interpreter runs about 20 to 30 times slower than optimized code. So that's really not going to get you any reasonable, it's not going to give you research results in time, and it's certainly not going to give you transferable performance measurements. So I built a baseline compiler. And so this is what you would expect from, imagine just building the simplest single pass compiler. So it just goes through the bytecode and generate machine code as quickly as you can. And the idea is that you can do full pass optimizations. And those will get you a number of things like being able to fold constants and eliminate null checks and things like that. But one of the key things is that the layout of the frames, the execution frames in memory is the same. So you can transfer between the interpreter and the baseline compiler because the execution frames in memory are basically the same size and the same shape. And so that means that you can go back and forth. So the interpreter may go up to compiled code, and that means that's because you're running code and dynamically optimizing it. You can also go back because you change instrumentation or there's some other reason to go backwards. So that's the main takeaway from that compiler is that it's basically, yeah.
But I want to get back to the thing with the baseline, so say 3x. But does that mean that it's 3x compared to an optimized compiler for the bytecodes?
Yeah.
Very important.
Yeah. Okay, so
That's
yeah.
still a big goal, but that's you have it already, I suppose.
Yeah, we're there. At least these benchmarks say that we're there. I don't know if that's true in practice. It's always about selection of benchmarks. Just to give you an idea of like, you can get pretty far with a baseline compiler. So it fundamentally boils down to abstract interpretation. It's like you make one pass through the code, and as you make a pass through the code, your abstract interpreter is basically computing everything that you would want to know to generate code for this one bytecode based on everything it's seen before. So it models the operand stack, and it also models constants and things like that. So as you're running through the code, for example, you see like a local.get, or you see an i32 const, you can manipulate the abstract stack, not necessarily generate code. So just an example here, just to flash in front of your eyes, like even though the bytecode might look like it's doing lots of work, all that's mostly happening in the abstract interpreter, and the sort of residual computation that's left over is what you emit code for. So that thing will end up generating like the pretty close to optimal. It's not quite optimal inner loop there. So you get pretty good code. And the gap between that and optimized code is this doesn't do a global register allocation. It does a forward pass register allocation. So it hasn't seen the future when it tries to pick registers for the machine code that's generating. So that's kind of important. That's one of the big advantages an optimized compiler has. All right, so then you end up there. So this is the two-dimensional trade-off in how much time you spend in startup versus how much time you get in terms of performance. You land in this area, which is the baseline compilers, there's kind of a Pareto optimization front if you're curious here. But anyway, so we're pretty close. So the 3x is in there. All right, now let's talk about dynamic analysis, which is probably, we're going to get close to doing something on the hands-on. I think we're probably going to have Elizabeth jump in here soon, but I want to give you just a preview of how this works in the engine. So the point of dynamic analysis is that you don't really understand programs until you're analyzing what they do. And in an interpreter, you have this nice property that you're running through and you're doing every single instruction. So the program is like very understandable, like the program instruction, there you are. So if you're curious about what's happening at some particular execution point, you get this nice mechanism, which is a callback. We call it a probe. And whenever this particular location executes, you can run a function. And the function can see a representation of the entire state. So we call that the frame state accessor. And then you can look at memory and the execution stack. So you can think like, as the interpreter runs along, do I have a probe here? If so, we'll do it. We'll run that probe. So this is implemented in the interpreter. It's like got some nice data structures. I think I'm going to skip over that. But basically, what we can do is that without making the interpreter any slower, we can just reserve an opcode for there's a probe here. If you insert a probe, you go and overwrite the byte of code and say that there's a probe here. So when the interpreter comes along, it's going to trip over the byte code and say, oh, this is where a probe is. Call the user callback. Because we've got a copy of the original bytecode, and also since it's an in-place interpreter, we know exactly where we were in the original bytecode. Like there's no offsets that we have to go rewrite. Instead, we have a copy of the code, so we know what code we should have been executing, what bytecode we should originally have been executing. And the great thing is we can also remove probes too, because we've got an original copy of the bytecode. If we want to shut that probe off, we could just overwrite it with what the original was. The interpreter will not trip over it. So there's certain dynamic analyses which actually make sense to be able to remove the instrumentation. So for example, code coverage, yeah.
Right. Yes, what you talk about now is the whole slides are together. But probe basically was a user-defined function, and it also gives it access to the current state.
Yep. So for the Zoom people on Zoom, the question was, the probe is a user-defined function that also gets access to the WebAssembly state. Okay, so being able to remove probes is nice because you might want to do something like code coverage. And so in this case, we want to know which basic blocks we've executed before. So as before, we're going to make a copy of the bytecode underneath. Again, this happens in the engine. It's not something that you see. We insert probes at all the basic block beginnings. And so then when we start executing the program, those probes will start firing. We're going to keep some metadata in our user-defined function, which records which of the basic blocks have been executed. And then as the probes start firing, they're just going to mark which basic blocks have executed. And then they can remove themselves because this is code coverage. We only care having hit it once. And so as the program executes, the probes fire, record that they've executed, and then they remove themselves, which means that you don't hit them again and again and again. And so eventually, when you compile this code with the JIT, all the hot code has already been executed. So it's naturally removed its instrumentation, and then you run fast. Okay, so probes are the thing, basically. That's all you need. That's the point of probes. You can build everything else out of that. So just insert the probes and they do different things. And we've built lots of tools in Wizard that all use that underneath. So obviously that goes slow if you're in the interpreter. So I won't belabor you with staring at machine code, even though that's what I do almost every day. But the idea is that the user code, which is JIT code, we can make it faster when we insert instrumentation so that it doesn't go through every layer of looking up the instrumentation. There's some optimizations that make that a little bit faster. So in the end, you might, for example, if you just want to count something, basically the JIT compiler understands you've inserted a counter and it should only insert 2 machine instructions to do counting. And so I glossed over the details of that. That's like probably not what everybody's interested in at like 9:40 in the morning, but yeah.
But just a quick thing here. For this, so it seems that what you just said is basically that the JIT compiler will look through the user callback and like inline it and optimize it. So, but how does it do that? Because I guess a probe is just a generic instruction, but I guess it does like a function pointer or something.
The magic is, which you'll see in a minute, is that the probe function can also be WebAssembly code. And because it's a WebAssembly compiler, it can compile the user code and it can compile the application of the instrumentation code together. And so Elizabeth's work has got a DSL that compiles the WebAssembly, and then Wizard does the optimization. Okay, so JIT intensification makes a big difference. Maybe that's something you can look up in the paper later. Okay, we can go write some monitor code, or we can go into WAM, because I think if we write monitor code, we might go down deep. It's up to you guys. I see some smiling people. I don't know what smiles mean. Is it devious smiles or is it grimaces of pain?
We don't know what the options mean, so we won't really make it fully on everyone's.
Okay, I think that's fair. I would say Elizabeth's presentation is going to be pretty fun, and it's going to make things a little bit more higher level, so you don't have to do low level grungy details. I think we'd probably get mired in details right away if we jumped directly into, right? Because this option would be, we're going to fire up Wizard source code, and we're going to like build Wizard and like write a monitor for it. And whereas Elizabeth, she's also going to do a live coding demo, but it's going to be using the DSL, which is going to be a lot more ergonomic. Yeah.
Be sure that we understand. So basically, writing a monitor is just inserting our own props and finding the user callbacks.
Yeah.
Like that.
Yeah.
So that's the low level details. Whereas one is a DSL where you're sort of a higher level.
Yeah.
That's the difference. Right?
Yeah. I see enthusiasm.
They're
everywhere.
both fun.
They're both going to be fun.
I want to see them too. That's why they're
Okay.
pretty interesting. But then I also want to so why don't you start with Elizabeth and leave that aside?
Okay. Yeah, that
Mine-
makes sense.
How about, mine could go kind of arbitrarily long. So how about you just like, do you have a simple monitor that you can show them?
We can look at some monitor source code because this is supposed to be hands-on. I think if we get into writing one, it could go off the rails.
Let's do that.
Let's do that.
That'll also let you.
Okay.
Using your computer while it's set up.
You will probably have to join the Zoom, by the way, so you should be prepared for that.
Switch over one time.
All right, so let's go into, you're looking at my favorite language, which is Virgil, which is Wizard is written in Virgil. So the point of,
Is it big enough?
is it big enough?
Okay, yeah, there you go.
I think actually, what is the simplest one? I can't see every one of my tabs. Okay, let's go into the memstats monitor. Okay, so the point of the engine instrumentation is that you can get down to every individual bytecode. And so you can instrument a bytecode however you like, and you can do things in the engine which are unnatural, which means that you can, for example, modify the WASM program. You can look at the WASM's program's representation. You can do everything at a level underneath. What this monitor does is actually pretty tame. It basically just looks at every load and store in the program and tries to keep track of statistics for which pages of memory are accessed by the program. So there's some code here. So you see monitor registry.add. It gives it a name. And this basically, there's basically a global registry where that name can be accessed from the command line to activate this monitor. So when you run the program, say monitors equals memstats, and this thing will get activated. Does that kind of make sense? So that's just what this first like 3 lines of code do. The monitor itself basically has a method that gets called when the module gets loaded by the WASM engine. So that's on parse. So we have module, and what it does, it creates an instance of this memstats instrumenter, and then that thing is the thing that goes and finds the instructions that will insert the probes. Does that high level picture make sense? So the code structure makes sense? Okay, so the memstats monitor makes the memstat instrumenter. The memstats instrumenter is a bytecode instrumenter, which is basically, if we go to that thing, oh, let's do this. Load it all. So the bytecode instrumenter is basically just a bytecode visitor. A bytecode visitor it has a visit method for every bytecode. So the bytecode instrumenter is basically going to go for every function, call one of these methods for every bytecode that it comes along. And so very naturally, you can override whichever method that you like and then do some work for it. So in our memstats monitor, for all load and stores, we're going to do this. We are going to insert a probe called a load probe. So in this first method, visit load, we create some stats thing. And if it is a 64-bit memory, then we are going to make a load probe, which otherwise we're going to make a load probe 32. And we insert the probe at that location. Same for stores. Memory locate, memory grow and memory init and memory copy and memory fill, they have different methods. And so the probe is just an instance of a class, right? You just write a class that extends some other class, and you write one of these methods like the fire method, and then it just basically calls something in our stats thing. And just to be clear, this is code that you write that is added to the engine. So it runs in the engine's address space. Like this is Virgil code, so all that goes on the Virgil heap. This is not code that gets injected into the program. And so that means that it can't alter the program's behavior. Okay, so the fire methods basically just hook up the stats to the bytecodes as they execute, and they're a little bit different, so copy init and so on. And the idea is that the memstats is where all the good stuff is. That's where all the record methods are. And you can see how it's like you're writing all the data structures. You're writing the thing that goes and finds the bytecodes that you want. And you're writing the thing that prints out this beautiful thing at the end, which I'll show you. So if we were to run this thing, we would just do this. And let's do this one. Might take a minute. And so all that is basically the loads and stores got instrumented and computed per page how many times was read, every page read or written, and dumped it out. There are a lot of other monitors too. So if I just point that out here. Yeah.
You show us how so go back and get some access to the state.
Yes, we can look at that.
Is it, I was doing the memstats such a test. That is something that you created, right?
Yep. Okay, so the init, let's say, look at one of these. So there's a probe class. which is here. And so if you extend this class and you override this method, you get this thing called a dynamic location. And the dynamic location is a thing that you can do various stuff with, one of which is you can get the frame. And the frame can give you a frame accessor, and the frame accessor has a bunch of methods on it. One of which is, so let's see, get U64 operand. The get operand method. So if we go into, I think it's an execute, to be honest. It might be, where did I put it actually? Oh, what are the frame accessors? Sorry. It is in WASM stack. Okay, so these are the methods that you can call on that object. So you can get the function, you can get the PC, you can ask whether this frame. So this is kind of like a mirror if you think about a mirror for a frame. And it basically gives you an idea of like, is the frame still valid? Because this thing could leak. You get it called in a probe, you could put that wherever you want. You could put it in a data structure, for example. You can ask the depth, which is like how deep are you on the call stack? You can ask for the caller, which will then give you the frame so you can navigate the stack. And so being a reified implementation of the stack, you can get like all the things. Like you can get how many locals are there, how many operands are there, like, and then you can start reading the operands and get the actual runtime values. You can also get the instance. So from the function, you can get to the instance, and the instance has a reference to the memory. So you can get to the memory, you can hunt through memory, you can hunt through the tables. So like basically all of the meta representation of the program, you can eventually get to through the function on the frame. Does that make sense?
Yeah, so basically, you get a really structured view of the current state. It's not
Yep.
like you get access to some kind of raw dump like that.
Yep, yep. And the point is that this could have a completely different representation if it was like an optimized code. So behind the scenes, like this thing is adjusting to what's going on. So I mentioned that in the interpreter and in baseline compiled code, the frame layouts are basically the same. So this is effectively going to do the same thing underneath. But like you can also alter things. So you can actually change the stack. So you can get the frame writer. And so you can actually change the value of a local variable or push stuff onto the stack. You could do various other things that are all of which are dangerous. And you could break the WASM type system. But if you did them responsibly, so if you responsibly did that, it might actually de-optimize and go back to the interpreter because the compiled code might have assumed a constant that you've now changed. So that's one of the things that is handled naturally by the VM.
Can the set operand be arbitrary? Like, does it?
And the
have to
set
go
operand,
as far back on the stack as you want?
it can, yeah, you can actually go out of bounds too. You probably don't want to go to out of bounds. Okay, so you get the picture. Like you can basically write engine level code, right? You could go do unnatural things to the representation of the program underneath. You could alter memory, you can alter tables and things like that. Okay, I think that's probably, are there other questions about that? Because I think we should seg to Elizabeth's stuff.
Just a question about unnatural things. So, does it have checks? Like, suppose you give it the wrong frame.
There are a few checks. One of the checks that it does, you mentioned, I showed it at the beginning, the unwound is unwound. Yeah. So there is a one guardrail is that if you get a frame accessor to a frame and then you hold on to it past that callback, it could be that this now represents a frame that is returned and unwound for some reason. So there's a check there. There are a few checks for updating locals. Like I think there's an actual dynamic type check. So for example, if you try to set a local, which is an I32 to be an F64, it will crash on you. And so you'll get a stat trace. So there are a few guardrails. If you try to access memory that's out of bounds, there's bounds checks on memory and things like that. But for the most part, there are definitely unnatural things that you could do that would crash. Okay, other questions? think we're ready for Elizabeth then. So I need to send you a Zoom link. Oh, you got it? Okay.
All right. Now I'm gonna share my screen. If you mute yourself, I'll just unmute. Okay, I think everyone can hear me. Yeah, that makes sense. Okay, so hopefully the internet doesn't get angry. There's so many things open. All right, I'm gonna give a high level overview of this framework called WHAM that we've worked together on. I'm going to be giving more of a talk on this, like from a research perspective on Thursday, if anyone's interested in kind of going more deep. But this is an overview from like a practical using it standpoint, and we're going to try and implement some monitors together, and hopefully the binaries that I put like work on your machines too, because sometimes you never know. But yeah, we're going to talk about how to build out observability and monitoring in this framework that uses, as Ben has mentioned, a DSL. So it's this instrumentation framework to try to reduce ecosystem fragmentation. And we've explored this in the WASM ecosystem specifically because there's some really compelling properties of WebAssembly that make instrumentation an interesting target for this. So for one, WebAssembly is a polyglot. And then, as you know, WASM is also a managed language, which runs on top of a virtual machine. And since WebAssembly is a polyglot, tools can theoretically be language agnostic. For now, we're targeting WASM for instrumentation, so it's kind of like really low level WASM monitoring specifically, but as we build this framework further, we can think about how to step up and look at this as like this language agnostic observability capabilities. Also, since when WASM is a managed language, the tools can be portable across machines. So you don't have to lock your tool into running on a specific machine. You can port it across, and then the engine itself can manage instrumentation. So you've seen the capabilities that Ben showed you where the engine runs your instrumentation for you, manages it. It can do dynamic insertion and removal of probes. So we're going to talk about what that looks like for this framework. So here's the high level view of this framework. You have some program that you're wanting to instrument. And then you have the expression of the tool or the monitor. I'm going to be like using those terms interchangeably. So you have your tool expressed in this high level, like aspect oriented style DSL. It tells you where you want to inject your code in this target program. If you're familiar with dtrace, it looks kind of similar to dtrace probes. And then since this is a DSL, we're wanting to keep the DSL from creeping the scope to this general purpose programming language. And since we're targeting WebAssembly, where you can compile a lot of different languages to WebAssembly, you can offload these more complex tool logic to these WASM libraries that you supply. So you've written your high level, like more complex tooling logic in the source language, you compile to WebAssembly as a library, and then WHAM can use this to do this arbitrary complex operation. Then you have the DSL compiler, and there are two different targets that it can use. The first target being the engine interface. So we've made this WAY, the WHAM engine interface. This is where it's literally interfacing with an engine. The engine inserts your probes and then manages your instrumentation for you. And this outputs this program agnostic tool.wasm. So you've noticed that the program itself is not an input to the compiler. And that's because it compiles this tool down into this program agnostic WebAssembly module. And it tells the engine, this is what I want you to do when you load a program. So find these points in my program, insert these probes. It's program agnostic. So then loads, finds those points, instruments, calls out to the library when you need to, runs on the engine. And this is really awesome because now you have all of the observability possibilities that an engine has. So even if you have like GC operations that occur, if you have like all of these different things that only the engine can see are now observable by the monitor itself. It's not just bytecode level observability. It's anything the engine can observe. It's also really fast because of some new optimizations that we've done specific to WAM. So you've seen there are some JIT intrinsics that exist for the native instrumentation for Wizard, and we've made some new optimizations for WAM specifically. So it'll see if there's a WAM probe that's been attached to certain points of the application, and it can do some interesting intrinsification there to make it fast. You don't have intrusiveness risks because the monitor runs in a totally different state space. The engine manages it for you, so you're not having to handle all of these different possible weird cases that you would have to handle if you were instrumenting at the bytecode level. It's also very portable. So this tool.wasm can port across different programs running the instrument because it's not specific to the program itself. But it's only portable for engines that have this interface implemented. So right now, the only engine that implements this is Wizard. So we're only able to run this type of instrumentation on that engine. But we're working with we've talked with engine implementers across different engines to try to figure out how to standardize this interface, because it would be a really great story for instrumentation in WebAssembly if we can do this. In the meantime, we have a bytecode rewriting fallback. So you don't have to instrument with the engine if you can't, and you can't run on an engine with this type of instrumentation support. So you can just rewrite your bytecode to inject all your instrumentation directly into that, which looks like this in the second target. So you take your program that you want to instrument, your tool, and the compiler kind of squishes all of that together into a single module. So now you have this application that has your like instrumentation code kind of scattered throughout it. And this is just more bytecode. So since it's more bytecode, it can run on any engine. Yeah, it's no lower level than that. So of course, you have some limited observability here because you can't see these engine-specific events, but you can see everything that's bytecode level. But it's really fast because it's just inlined into your program, all of these different new instructions. There is some risk of intrusiveness, but this is kind of like a guarantee of the framework itself to hopefully not mess anything up. But of course, like there could be some unreachables that are reached in your instrumentation code. If you're running this in bytecode rewriting context, then you would have to handle that somehow, and you can't handle an unreachable. But if you're doing this engine instrumentation, you could handle an unreachable that happens in your tooling code. So you kind of have to think about like intrusiveness in that type of terms. And then, of course, portability, it runs anywhere. It's just more bytecode inside your bytecode. So yeah, 2 different targets. WAM takes care of it for you. So a high-level view of what this engine interface looks like. You have your app.wasm you're wanting to instrument. You have different events that you're wanting to instrument inside it. So let's say you want to instrument all the calls. This can be other bytecodes as well, but specifically in this example, it's wanting to instrument calls. And your monitor.wasm is what tells the engine, hey, I want to match on all of the call opcodes. And when you run me, I want you to specifically pass this subset of application state to me because I depend on this to do my piece of functionality. So this is going to pass the first immediate on the opcode, which in WebAssembly, the call opcode has an immediate of the FID that it's targeting. So if it's targeting function 0, then that value is going to be 0. The arg0 is the top of stack. So it's the first argument that comes into that call, and you want to pass that on probe invocation. So when this gets invoked at runtime, when it's been reached, it's going to pass that state to it as just like operands to some WebAssembly call. So we've instrumented all these points in the application. When it reaches this call, it invokes and passes the immediate and argument. And then it continues back and continues running my application as normal. And what makes it fast here is that you have this specific subset of application state that you depend on to do your probe operation. And you're not having to create this really expensive giant frame accessor that Ben showed you before. Instead, it just passes the specific pieces of information that are interesting to this probe, and it can run and then pass back the continuation. And so all of this can be recognized and optimized with intrinsics in either like any of the tiers inside Wizard, which the tiers that we're going to show you are interpreter and JIT, or the baseline compiler. Yeah, so you can observe that this is just a static constant, stack location, intrinsify, notice this, pass it really optimally. Another thing is that this is just WebAssembly code. You're not having to do anything really special in the engine to handle this. You can kind of just use the same optimizations that you already have inside your engine to make it run fast. And through your intrinsics, you can go as far as inlining this arbitrary WebAssembly code into your JIT application. Yeah, runtime calls are expensive. So how can we remove these runtime calls? And runtime calls, I mean like calling down into the engine. We want to remove these. In the interpreter, we can accomplish this through what we're calling the trampoline optimization. This is kind of overlaying on top of it, but yeah, you can see that. So you have the trampoline where when calls occur, the interpreter has some machine code stubs that are generated at load time. So you have the transfer. So this is bundling the arguments that you're wanting to call your probe callback with. In this case, I showed was the immediate arg0 and arg0. Then you have invoke. So it's going to invoke this probe callback and then continue things on in that original application. And it'll do this for all of the probes that we've generated. What's happening? There we go. And then in the JIT, that kind of similar machine code step, that's just inserted directly after the call. So you have bundling the arguments, invoking the probe callback, and then continuing on your application. This is called the WASM to WASM optimization. And then we have the inlining optimization, that now all of your probe function just gets inlined directly into your JIT application code. So we don't have any calls at all at this point. I'm not going to show charts to show how fast this makes it today, but if you're more interested, like I'm going to talk again on Thursday on this. So here's high level of the DSL. So this is how we say, this is what I want you to do at these points of my application. So this is the entry point to the framework, how you express your monitoring, and then the compiler itself figures out how to inject your code. So here's an example monitor in WAM. This is like a tiny little example snippet. It's for doing like branch profiling, but in this kind of weird, interesting way. So if you're thinking about like a branch profiler, this is trying to see what the hot branches are in your code. So figuring out which branches are taken and how many times as your code runs. So we have some global state here. Over time, it's going to be accruing whether or not like what branches were taken and how many times they're taken. This is telling you where I want to match. So specifically, I'm wanting to find all the BRIF opcodes in my WASM module. This is saying when to insert. So this is interesting for bytecode rewriting more than the engine interface, but it'll find the BRIF and then insert your probe body before this BRIF. These are constraints. This is kind of like an example constraint, but you wouldn't necessarily want to, it just kind of depends on your monitoring use case. But as an example constraint, you can constrain the match to specifically only insert a probe if you see a BRIF at the PC offset of 25. So this is like the number of bytes into your function. If I'm at PC offset 25 and I see a BRIF, I want to insert this probe. And this is the like logic to run. So this is the body of my probe. You'll note that this is using the top of stack. It's also using something called FID and PC. And none of these are declared. And I'm going to show what that looks like in a bit, but these are like called bound variables that are bound by the event that I'm targeting. So WAM supports glob matching. So if I'm wanting to instrument and match on more than one event, then I can match with globs. So it'll only match on events that match these globs. So all of the WASM load and store opcodes as an example. And at all these things, I want to insert this body. It also has really powerful storage classes. So we have, like I said before, bound functions and variables. This has not been declared anywhere inside my probe body. Instead, it just magically appears and I can use it. There's a capability that we have for the command line of WAM where you can kind of query for bound functions and variables based off of this match name. So it'll find like, oh, on my WASM opcode i32.load, I have a data size bound variable, and the data size for an i32 would be 4 because I'm going to be loading 4 bytes from memory, basically. I can't hear you very well. You have to talk a little louder. Yeah, if it doesn't have this data size bound in that opcode, so if I did WASM opcode star, then it's going to match on some opcodes that don't have a data size bound there. And it's just like the compiler is going to say, I don't know what that is. Yep. Yeah. Yeah. Oh, I also have derived variables. So the effective address, that is the address that I'm actually going to load or store from in my, like when I run this application code. So in WebAssembly, on a load or a store opcode, you have a static offset inside your memory, and then you have a dynamic offset. So it's the static offset plus this dynamic offset that winds up being my effective address. So it'll compute that for you, so you're not having to do that computation inside the probe itself. There's also probe local state. So in when I insert this probe, each probe will have an instance of both of these hit and miss variables. So so this is unshared. So between probe instances, they're not shared. It has its own instance of this variable. It's not going to be reinitialized on each entry. So the hit and miss variables will stay true to their last value when you re-enter this probe body. I haven't implemented this yet, but this is what we're going to do eventually. We have shared variables as well. So let's say you want to see hit or miss across all of this type of opcode, like the load and store opcodes, then it's the shared variables between all of these instances of the probes. We also, like I said before, you can offload more complex logic to these WASM libraries that are supplied to the DSL. So this is how you would import one of these libraries and then use them. So you can see this is where the import occurs, and then it uses some function called check that is exported by this WASM module. Does anyone have an idea of what this script does? So we're using some library called cache. I'm loading all of my load and store opcodes. I check on the cache for some address that I'm either loading or storing with the data size, get some result. Right, it's a cache simulator. So it's simulating some cache hit or miss lookup. It's not actually like doing a cache. It's looking up on my simulated cache. So this cache is supplied as a WASM library. So I can supply some arbitrary implementation of a cache and then see what my hit or miss rate would be based off of this implementation of my cache.
Let's say I'm writing part right now. Simulator would be part of the simulator could be this.
Yeah, so you're seeing what your performance would be on your cache based off of like this monitoring. So doing this simulation, seeing what would happen. Another thing that I didn't highlight is we have this report functionality. So these are the pieces of information that I actually care about. This is kind of like some local state that I need for my probe to run, but this is the output that I actually care about, this hit and miss cache rate. So report, you can just tag variables that you care about with your report keyword, and then it'll automatically flush this at the end of your program executing. And it does all of this for you. You don't have to worry about it. Anybody have an idea of what this does? So we have this global state for report variable. It's matching on all of the WASM opcodes, and it's incrementing some category ID, which is a bound variable. So yeah. Yeah.
So this category that you showed us, like, it's actually part of the ESL. It's not about.
Yep. I think there's a few more categories that are put inside this as bound variables, but at a high level, yeah, it's like this. I have this many load operations, this many global gets and sets, like those types of categories. Yeah.
On those categories.
No, they're kind of just like defined by me. I need to make it to where it's configurable, but that's beside the point. Yeah. So the reason why is because if you're at like the boundary for some like block, is it called a block? I don't remember. Inside a cache, a what? Cache line. If you're like at the boundary of a cache line, then you would technically have to query two across the line. So there could be 2 hits or misses. Yeah, it's like a minor detail. Another thing that I need to make better, if you notice, I'm having to like do some binary manipulation, and that's because WAM doesn't support pooling 2 results. So I'm having to like, what is it called? Bit pack them. So I'm pulling the 2 hit and miss result with the bit pack, but we'll get there. Give it time. Oh, the result. Sorry. I'm like pulling out the bit packed values.
Oh.
Yeah. So we'll get there.
WASM supports multiple returns.
It does. WASM does. It's just WAM doesn't. Okay, so let's write some monitors together. We have 10 minutes. So I will do my best. If anyone wants to see like more examples, feel free. I'll show you later. But let's like get set up. This is the repository. I'm gonna like run through these on my machine and you can follow along with me. And hopefully I built it to where you can run these things on your own machine. I have binaries that should work on Macs, and x86 and x86 64. So if you have some other machine type, it will not work with you, but
Yep. We're gonna repeat what we did. So.
yeah. Unless you really want to see the same thing again.
It might be more polished the second time.
Sorry, did everyone get a chance to like pull up this module or repo? Okay, I don't see any more phones up, so I think we're good. All right. I think I need to make this way bigger. Still tiny. Wow. I guess I could send the link over Zoom. Where is Zoom? Okay, it's not working. All right. Oh. Oh, it's sharing. Okay, I need to make it share the screen. This one. Okay. Oh, this is so big. All right, so at a high level, we have a README that's going to walk you through some stuff. So we will not have time to do all of this in 7 minutes. I'm so sorry, but you can kind of do this on your own. If things break, please tell me because I will fix it. But here's the README. Feel free to read through this when you have time. There are a bunch of binaries in the bin directory. So we have the WAM binaries. This is what the CLI is for WAM. This is how you're going to query on these match rules that I said before, and how you're going to be able to instrument your applications, either with bytecode rewriting or targeting the engine interface. Then we have all the wizard binaries that you should need. So if you're running on a Mac, you should be able to run the JVM binary, and then you have the x86-64 and the x86 Linux binaries. Then we have the libraries. So these are going to be these like libraries that the WAM DSL can call out to if we're wanting to have like more complex logic in our probes. Then these are going to be the monitor implementations. And the only one that's fully fleshed out is the branch monitor. So this is seeing the hotness of branches that are taken in your WASM program. Everything else is empty. So we're going to write the code together. And these are some example applications that we can run with our instrumented variations of them. You'll note that if you run this on a Mac, it's going to be super slow. And that's because it's Wizard compiled to the JVM. So if you're running, it's like literally Wizard is being run by the JVM, and then you're interpreting WASM code on top of it that is monitored. So it's like super slow. So if you're wanting to like run a faster one, I think the fastest is like branches.wasm because I hand wrote that. And then I think ADI.wasm is pretty fast too. But anyways, we have 5 minutes.
Do it.
Let's do it.
How many people have actually got stuff downloaded?
One.
One person?
Sweet. I will just like live program and that you can like watch along. Oh, you don't need to build anything. I have the binaries in here for you. I might have said in the README to get WASM tools, but you don't have to worry about it. Okay, so this is the branch monitor. We're gonna see, hey Alex. We're gonna see what branches were taken out of the total possibilities. It's kind of like gonna let you calculate the percentage. And then this is the BR table. So this is matching on all of the BR ifs, then the ifs, and this is the BR table match. So as an example, we're gonna show wait, and all right. So this, can you even see that? It's so small. How do I make this bigger? No. Okay, well, so sorry, this is so tiny, but inside this, I'm running my WAM binary and I'm passing a rule with the -- rule command and or option. And then this is the rule that I'm trying to query in my WAM binary. So it's going to, oops, I forgot to do this. Pass the command. So inside this, it's matching on all of these things. So it takes the match rule and figures out what will be matched and all the things that we bound by this guy. So WASM just matches the WASM provider. There are a bunch of different bound variables for this. So this will help you write your scripts or like know what bound variables you can use to write your scripts. This opcode, it's not a glob, so it matches on the opcode package. And there is this specific bound function if you want to use it. This star if is a glob, so it's going to match on multiple different events. The if event is the if opcode in WebAssembly. There are several different bound variables. Inside this, I use arg0, and I think that's the only bound variable that I use. So I'm going to be using this, which is the top of stack. The opcode, the operand to the opcode at index 0. And then the star if also matches on the brif event. And this also has arg0 provided. So like you said before, you need to make sure that the bound variables are bound for all of the matches. And then this is the body. So it's checking whether the branch was taken based off of the top of stack. So I guess we'll have time to only run this. And if we want to if you want to see the other monitors that I have in this example repo, come by me and I can show you. So this is the expression. It's pretty high level and intuitive if you know the semantics of WebAssembly. So I'm going to run this. And I went ahead and did this to make it a little bit faster. So to run, I'm just running my WAM command line tool. I'm wanting to instrument with this script. So it's this branches script that we're looking at right now. And I'm wanting to target this application, which is at this location. So when I do that, I have outputted a WASM binary. So that's if you remember in the architecture overview, it had the app.wasm that was green with like all the red dots on it. So that's what this output.wasm is. If you want to, you can use WASM tools to actually print this output.wasm file. And you can see like all of the instrumentation that was inserted. So this nope. All right. No, I did that wrong. Okay, so this is the original application. It's like pretty short. It's 125 lines of WASM code. But this is doing quite a bit behind the scenes. It's creating an instance of these variables per probe location, and it's going to flush all this at the end. It's going to wrangle your arg0 while keeping the stack good over time and doing all this crap. It's also like talking to a map that's provided by the WAM library. So this was the uninstrumented version, huge or small. This is the instrumented version. So it's doing a lot of extra stuff for you in the background, and it'll flush all of this when the program finishes executing. So the way that I would run it is I'm going to run this on top of Wizard because that's the binary that I have. Want to have a multi-memory because WAM does depend on multi-memory. This is actually an environment variable that's passed to WAM to tell it to print to the console when it does my report flushing. This is using the WAM core library. So I'm offloading all of this printing stuff to something that's been compiled to WebWasm. And this is the instrumented application I'm wanting to run. So when I run this, it flushes the CSV, and you can do some post-processing to build out some visual representation of this monitor. But yeah, we're past time by 2 minutes, so I can't show you way unless you want to stay behind, but that's kind of like an overview of this framework and what you can do to build out such like low-level tools. So yeah, thanks for coming, guys.
Any questions? I guess there's caffeine out there.
I hope so.
Sure.
Remember those days of OEM, guys?
I do remember the
Years
days
ago,
of,
That's right.
I remember the days of
Um,
LVM and Jikes.
Now that's 20 years later, and I mean, yeah, you're in it for awesome. What are the different lessons, without repeating the same mistakes? of what they used to do?
How long of an answer do you want?
That call.
We can talk at coffee. So I think, sure, it's a different domain. WASM certainly learned some lessons from the JVM. The interesting things here are that WASM is a lower level computational target, so there's many new languages that are coming to it. And so it becomes a little bit more universal. I think there's some engineering problems that are different and more fun with WASM. In particular, I think that baseline compilers for WASM are like way better than they are for Java because it was designed to be able to, you can do forward pass abstract interpretation because of the design of the bytecode. So you can do lots of things. So there's some immaturity in the WASM ecosystem, which is just means that there should be some engineering investment. I'm in a research capacity now. I used to be in industry, and so I have to eke out a little bit of what the research contributions are. I think there's some things in the cracks, but I think what I'm most excited about is actually where we're going with the specification. So I'm not an expert in spec tech, although I work with all those people. And what I foresee is a vision coming from spec tech to actually starting to generate the things in the engine, doing that automatically in a way that's like actually proven each of the steps along the way. So that's what's exciting about to me. I think the specification technology has advanced so much from where it was in the JVM land. Also, there's like tons of WASM VMs. People like write them as bachelor's theses. So that's like a fun thing about the ecosystem. So many things to play with. But we should chat more. All right, thanks everybody.
Thanks.
Okay, there are two people on the Zoom, but they were here in the previous iteration, so they're just gonna have to deal with it. All right. So you guys know who I am. I am not Elizabeth Gilbert or Conrad Watt. So we're going to talk about WebAssembly today. This is going to be more hands-on. We're going to mostly work on things that both Elizabeth and I have developed, but we're going to talk about lots of things in the space, lots of tools in the space. But I figured I'd give an overview of WebAssembly stuff that gives you enough context so that what we're doing makes sense. So WebAssembly, typical spiel, it's an efficient low-level portable bytecode. It gives you close to native performance. It's got an extremely rigorous specification. Many languages are already targeting WebAssembly. And I say that it was born on the web. So like many German names, which are named for where things came from, WebAssembly is named where it came from. It runs other places too. And personally, this is one of my hobby horses. I think WebAssembly is the best candidate so far for a universal bytecode. And so there's a amusing little story that I came up with some help from my AI friends. So imagine you have a lamp and it's got a very simple interface. It starts off with a toggle command. And this is designed by hardware people. And the toggle command gives you the state back. But suddenly is fully programmable and it has its own scripting language. And it was just a lamp. How did that happen? And so this is a bit of a rhyme. So back at the start, there was a lamp. Then we made toggle and spec'd with a stamp. So it kind of makes sense from a hardware point of view to have this interface because toggle is very primitive and it gives you the previous state. So if you write a specification, you need a specification language. And what better specification language than German? So fordert die Lampe auf, den Zustand auf 1 zu ändern, wenn der aktuelle Zustand aus ist und umgekehrt. Gib den aktuellen Zustand zurück. So if you understand German, you'll understand what that means. And one of the key things is there at the end is that it returns the current state. And so you might actually have to read the spec to find that out. But toggle alone meant 2 calls to check because client insisted on off with spec. This also happens a lot. So maybe toggle wasn't what you actually wanted. You actually wanted to be able to just set the state. And of course, that's possible. The way you do that is you actually toggle once to find out what the previous state was. And if the state is wrong, then you toggle it again. And of course, you need to specify that too, because you now need to tell people what to do. And so in German, they might say, spec says this is advice. Basically, do it yourself. Roll your own version of on and off using the thing that we gave you. Of course, this requires you to potentially do 2 commands, right? So that's twice the latency. And there's also race conditions too. If you've got 2 people trying to set the state, now you got a problem. Soon perf pressure they could not resist, and set on off was next on the list. So they decided because of race conditions mostly, latency also matters too, but maybe we just add a new primitive operation, which is set. This needs a specification too. Fordert die Lampe auf, ihren aktuellen Zustand auf den angegebenen Zustand zu setzen, entweder ein oder aus. Gibt das Ergebnis des Setzens des Lampenzustands zurück, das entweder Erfolg oder Fehler sein kann. And if you understand German, there's something waiting for you here. But the key thing is that we managed to meet our performance requirements. We reduced latency, and so everybody's happy. But that last bit at the end, it can fail. And so you maybe only get that if you read the specification carefully. Soon they discovered that, oh, well, if you can add set on and off, maybe you can add other features. Then came new features, all in a flurry. All we could do was spec in a hurry. So now it tells time, right? It's a great thing that you'd be able to, market your thing that it tells time. And now the dam has been broken, so we're adding features all over the place. We not only have a clock, but we have the ability to store data. So now it's like a file system, basically. And all those things need specifications. And the thing is about writing specification languages, there's gotchas hidden in there. There's underspecified things, and there's things that are really dangerous. Soon, behold, a language, oh neat. Next thing you know, it's Turing complete. So you just keep adding features until eventually there's something that causes you to be Turing complete, like a lambda or something like that. So now you really do have a lamputer. And once it's Turing complete, you decide, I don't like LAMP script. It's a dumb language. How about compiling to LAMP script? So you have a Python compiler and a JavaScript compiler, Java compiler. We thought we were clever, but it turned out a mess. WASM's clean core would have saved us the stress. So the point is that we have a thing which is Turing complete, and that's the WebAssembly bytecode. So this is kind of my hobby horse, is like we should use the WebAssembly for this. So programmability is tending towards Turing completeness. There's a bunch of intermediate steps, and there's a lot of weird VMs out there. And what if we could just all use WASM? And that's kind of like my mission to some extent. And we'll move on to the rest of the content. So hold on a second. Let me check the chat. Okay. So back to WebAssembly. Yes, there's like lots of papers behind it. So this is not just a thing that is used in industry, although it is picking up, but there's lots of papers behind this. People are working on the specification. There's a lot of increase in the specification technology. And I think this actually really affords us an opportunity to go towards a VM that is fully verified. And so we're going to talk about some of the tools in this space that have been spawned out of the research behind WebAssembly. Just to bring context here to how WebAssembly code is structured, the code comes in modules. So they're binary. There's a text format for them as well, but they're basically structured in this way. They come in different sections. So there's types that are declared in the module. There are imports and exports to the module. There are function definitions. Excuse me. And ultimately, it's a type stack machine with structured control flow. One of the great properties about WebAssembly is this encapsulation property, where a WebAssembly module, which has computation and potentially state inside, it can only talk to the outside world through imports and exports. And so the core instruction set really talks about like a computational model. It doesn't talk about a system interface. So it's really about sandboxing untrusted code, and what you give to the module is kind of up to you. So just to illustrate what if we can make this go away. Just to illustrate what the instruction set looks like. So there are over 540 instructions in WebAssembly now, in WebAssembly 3.0. That seems like a lot, but if you group them right, it's actually quite manageable. And so we'll go through what these groups are. This is the grouping that I came up with. So you've got a couple of instructions here that are mostly just delimiters for like structuring the code. So there's literally a no-op instruction. But instructions like block and loop and end and try table, these basically just delimit control flow regions. They don't actually do anything. So they're not too bad to worry about those. Then there are actual instructions that do control flow. So there's an unreachable opcode. This is basically if you have some branch of your code that's like maybe a safety check has failed, you put an unreachable there. And then there are instructions to do actual control flow, like local control flow, if and else. You can throw exceptions. You can do conditional branches. You can do multi-way conditional branches. You can branch on null. You can combine and cast with a branch. And then there are also control flow for dealing with lightweight continuations. That's actually an extension which has been proposed. It's not part of the standard yet, but this is all in the sort of control flow category. And then for dealing with calls in between functions, calling and returning, 3 bytecodes, a direct call, which is the call instruction, an indirect call, which goes through a table, which is call indirect, and a call to a first class typed function, which is call ref. And then there are tail call versions of those. So return call, indirect, and return call ref. And those are basically the same thing, except they delete the caller frame before they do the call. So you can actually do, functional programming and not blow up your stack. Then we've got the basic data flow instructions for dealing with local variables in the operand stack. So you can drop a value off the top of the operand stack. You can select between 2 or more values on the top of the stack. Without doing control flow, you can read and write the local variables, and then you have constants. So if you just look at that, I think that those are actually the most complicated bytecodes in my opinion, because those define all the core abstractions of the control flow and how functions work and things like that. And the rest of them actually scale out quite easily. So we've got storage, so unmanaged storage. So we've got global variables in WebAssembly, so you can read and write these. These are not aliased in the memory. You can only talk about them statically by an index. So you can't accidentally have an errant pointer, right? They'll overwrite a global variable. Then you can have tables, which are basically references. So tables are not aliased with memory same kind of thing. You can't have an errant pointer right that overwrites a table. You have to talk about the table entries individually. And then memories are actually the low-level storage mechanism. So that's byte-oriented storage. It can be big. It comes in units of pages, and there's lots of instructions to deal with memories, which are very low level, like write a byte, read a word, read a whole vector, where a vector can be 128 bits, and so on. And so all of the instructions associated with those storage, you can pretty much just put them in that category, and they don't have anything to do with control flow. So you can think of them in their own way. Then we've got, so with the GC extension, which is now actually part of the standard, as part of the WASM 3.0 standard, now we actually have managed data structures. So we have fixed size structs, which are effectively records that have width and depth subtyping. We have dynamically indexed arrays, and we have typecasts and type queries between them. So it's a statically typed, low-level object-oriented system. There are no methods, and like method dispatch is not part of this. You build virtual tables and things like that. But these go on a separate heap. They're not aliased by the memory. So that means that you can't accidentally overwrite a struct somewhere and like cause a memory corruption. So these are the two things that give you the storage abstractions, like the mass storage abstractions. And then everything else is basically just arithmetic. So you've got integer arithmetic, both 32-bit and 64-bit. So like all your typical things, add, subtract, multiply, and all the fancy bitwise stuff. You've got IEEE 754 floating point. So you've got all the things that you would typically find in a CPU, and these literally map onto CPU instructions. So you don't have a lot of work for the VM to do. It basically just has to generate the right machine instruction. And then we've got this huge pile of vector instructions. And so these are vector values are 128 bits in WASM. This is effectively the intersection of the three most popular vector instruction sets, which are basically ARM, x86, and what's on RISC-V. And there's like, it's a bit of an eclectic collection because it is that intersection, but you can think of it as like, if you have four 32-bit floats, you can do a parallel add on them and multiply and so on. And there's a bunch of instructions for selecting the different lanes and mixing them up and doing things like that.
RISC-V, the vector instructions are not in the core, but they're one of these sort of things that are added on that are most likely going to become like a standard profile that's formalized next year. Can we think of all this vector arithmetic the same way that it's like an extension before, but it's like should be there for all time?
Technically, they are part of the spec in that there's not any profiles, but we are talking about having profiles. And SIMD instructions are one of the things we'd like to put in a profile, because just the nature of the instructions, emulating them in the VM is usually not any faster than scalar code. So it's better to not have vector instructions if the hardware does not support them. So it's better to actually know that there are no vectors and you do your own scalar arithmetic. So that's one thing we've talked about. Also, WASM GC is actually quite nicely factored in that it could also be a profile. For example, like on an embedded system, maybe you don't want to have a garbage collector if you're not using it. Right? So even though it's part of the instruction set, maybe you can turn it off. Yeah. The profiles are meant for agreement between tool chains and the VM, so that this profile has exactly this set of instructions, so that tool chains that target a profile and VMs that implement a profile agree on what that set is. You can't. Yeah. The VM, yeah. The VM would tell you what profiles it supports. Okay, so there you go. All the arithmetic you'll ever need. We'll never need more instructions, he said. But we're adding more instructions because it turns out there's always one thing in a CPU that makes something goes fast. Anyway, okay, so if you think about WebAssembly in a nutshell, it's basically the instruction set architecture and the data model. And the instructions are all of those, so I factor them that way. And then you've got your storage stacks, globals, tables, memories, and the heap. Okay, so research tools for WASM. So there's lots of different directions that WASM research is going. Elizabeth and I, we basically work on engine stuff and work on instrumentation. So when we get into the tutorial, we'll talk about those things and we'll actually do examples in that. But I wanted to mention a lot of these other tools because there's also people around that can talk about more of them in detail. So as far as the specification goes, I mentioned SpecTech, or maybe I didn't mention SpecTech, but SpecTech is a DSL, which is a recent development, which is literally a DSL only for writing the WebAssembly specification. And so it has the ability to write like inference rules, and you can build a type system and also specify the binary format and all that. So all of that is in a DSL developed to write the specification. That DSL also generates the prose that you can read. The actual PDF document comes out of that. So that's a whole interesting research direction. The people who are working on SpecTech are all here. So Andreas will be here, I think, tomorrow. And there will be a whole session on Thursday morning. Andreas will give a talk about that, which is basically a tutorial about how SpecTech works. But this is like the future. We now actually have a machine readable specification of what WebAssembly means. Prior to that, there were two different independent mechanizations of the specification, both in Coq and Isabelle. And the specification prior to that was basically written in LaTeX with the typical inference rules and things like that. So that's kind of where the specification is. It's like, this is like cutting edge PL technology. As far as verification, there's been some tools that have been built. So one of them is Iris WASM. Also, I'm not an expert in Iris, but this is more if you want to verify application properties. So you can actually specify, you want your program to have this, and it will actually check this against the real WASM spec. Okay. If you're interested in benchmarking WASM, this is like a whole deep thing. So how do you measure the performance of different engines? There are a lot of different engines. There are a lot of different benchmarks that you could run. There are a lot of configurations. There are a lot of different machines. I had a student work on a tool called WASURE, which is basically measure with the MEA replaced with the WA. And the idea is that basically is just a manager for all the different engines and all the different benchmarks. And so WASURE is effectively a thing that makes it really easy to get lots of different engines installed and run the different benchmarks and compare them. It turns out that that's not a solved problem. Benchmarking WebAssembly is not a solved problem. I won't go into a lot of detail about that, but you can imagine there's a lot of different languages. There's a lot of different program behaviors. There's a whole instruction set architecture for like how do SIMD programs run, how do WASM GC programs run. So I think that there's still some research to be done there. As far as fuzzing, there's a bunch of different fuzzers out there. I've used a couple of them, and these are mostly fuzzers that generate WASM programs as opposed to fuzzing the WASM program's inputs. But these are quite useful if you're developing an engine and you're trying to break that engine in order to find and fix its bugs. And so there have been a number of papers on that. If you have test cases that, for example, show a bug in your engine, which happens in my world a bunch, there are tools specifically to reduce test cases. So like WASM reduce, for example. And I mentioned binary N. Binary N is basically a big bundle of a lot of different WASM tools, including an optimizer. So this is a WASM to WASM optimizer. You give it the WASM program, it does stuff to it, and you get a faster WASM program. WASM has a strict specification, so there's certain optimizations that you might consider doing that wouldn't strictly be allowed. For example, can you reorder memory accesses? And the answer is you can only do that if they don't trap and they don't alias. And so it's a little bit difficult to prove that two random memory instructions that access addresses aren't aliases. So if you flip a flag on binary N that says, assume that, for example, memory accesses don't trap, because that's the other interesting case, you can have it do more optimizations. So there's a bunch of things in there, flags that you can flip in binary N in WASM opt to make it do things. For example, assume that this program is actually closed world. And so that makes a difference for how the WASM GC type system works. So it can do more optimizations for WASM GC programs. And there's also weird, I wouldn't say weird, but there's certain restrictions on floating point arithmetic that just fall out of IEEE 754 that you can't optimize those things. And so this is kind of like equivalent to like F fast math and GCC, which is like assume that you can do commute floating point operations and things like that.
Just back to the translation of Would you say that difficulty of that problem is compared to the problem with C? Is it easier or harder on C?
Is it harder than C? I don't think it's harder than C. No. One of the great things, so this RR reduce I mentioned in the next line, that's actually a paper that we have in ASE. You can use record and replay to do test case reduction as well. And so that's what that paper is about. WASM R3 is this replay framework that we came up with that WASM has this nice property that you have this separation between what's inside the module and what's outside the module. The WASM module cannot access anything outside its module unless you import it. And so if you think about that boundary, that host WASM boundary, you can record stuff at the boundary and then take the WASM module and replay the effects of that outside code as long as you know any side effects. So just to kind of paint a more clear picture about that, imagine that you share the memory of the WASM module with the host and you call a host function and the host function changes something in that shared memory. Well, you then later run the WASM program without that host and you don't get those updates. But there's a relatively easy way that you can record the difference, which is just make two memories where there's one memory that the WASM module has that's private. It does all of its writes to both copies, but the host only writes to one copy. And so when the WASM program reads, it reads from both and compares, and it can tell, oh, I didn't write this. It came from the host. So with that, you can automatically derive a trace of, oh, I call this host function, and later on, I observed that memory was different. So without instrumenting the host, you can actually get a replacement, a replay of the host's behavior. So that thing that we developed allowed you to just like go to a web page and visit it and then run the WASM code on the page and then get a WASM module, which was the original module plus a replay of all the thing that the web page did. And so you might use that, for example, to make a benchmark out of a game. And so now you have like the program, which is the game, plus all the things that the web browser did. And so that's really nice because of this separation. Okay. There's a bunch of engines out there. Obviously, every web browser has its own JavaScript engine, which includes a WebAssembly engine. So V8, which is in Chrome, SpiderMonkey, which is in Firefox, and JSC, which is in our JavaScript core, which is in Safari. And they don't share any code with each other. They all have their own compilers, their own parsers, and everything. But they also have their own command line interfaces. So you can actually build these and run them outside the browser too. So if you're doing WebAssembly stuff, you don't actually have to run everything in your browser. If you care about V8's performance, you can study it outside. Obviously, Node, which includes V8, you can run WebAssembly code too. There's a bunch of other standalone production VMs: WASM Time, Whammer, WASMer, WAS0, WASM Edge, WASM 3. They all have almost none of them share any code with each other. They have their own parsers, they have their own compilers, their own interpreters. In particular, WASM Time is written in Rust. It's got actually quite a bit of market share, mostly used for cloud and edge stuff. And so it mostly does ahead of time compilation. Whereas Whammer is like more of an embedded systems VM. And so it also has its own compilers, and it's a smaller memory footprint. WASM 3 is an interpreter. So it basically takes WASM code, rewrites it to an internal format, and then interprets it. And it has the lowest memory consumption. So it's also quite hackable. It's got very relatively clean C code base. So you see a lot of people hacking both Whammer and WASM 3. In the research space, so Wizard, which is we're going to talk about today, that's my engine, and many other people have worked on that. And then like you can find random papers that, oh, we did a thing and we like made our own WASM engine. So for example, if you guys have heard of the copy and patch compilation paper, one of the things they did is, hey, let's do a WASM implementation. And that's what WASM now was. WASM Time is written in Rust. WASM is I think most of it's written in Rust. WAS0 is written in Go. WASM Edge is written in C++. WASM 3 is in C. Whammer is mostly in C. Wizard is written in Virgil. WASM now is written in C. As far as instrumentation, which is most of the stuff we're going to talk about today, so there's an instrumentation framework called Wasabi, And so this basically will inject calls to imported functions wherever you like in a WASM program. And then you can implement the imported functions in JavaScript. And so you can then run your instrumented WebAssembly in the browser or in one of these command line JavaScript engines and do what you want there. It has a reputation for being kind of slow because calling JavaScript for everything that you want to do for instrumentation is a bit slow. There's a new thing called Wastrumentation. So there's a paper about that at eCoop. This is a framework where you write your instrumentation in Rust and kind of some interesting macro foo in Rust, and it will inject your compiled Rust code as WebAssembly into your WebAssembly. So it's like WebAssembly with WebAssembly instrumentation. And then WAM, which is mostly Elizabeth's work, is a DSL, which you can write instrumentation in, and it will either inject bytecode or it can generate stuff for an engine that supports separate instrumentation. And so we're going to actually demo that today. Okay, any questions about that? That's like, I'm not going to go a whole lot deeper into those things like Iris. I don't know a lot about Iris, to be honest. We're mostly going to talk about the instrumentation stuff. Okay.
Wasabi sets some expectations. Just the name. Probably very strong implementation.
Yes, it makes your nose runny. I don't know. But Wasabi being very slow means it's very nice to publish papers and compare against them. Okay, so I was born in a I cannot pick the year that I was born in, and that determines the year that you go to grad school. When I went to grad school, Jikes RVM was all the rage. And so Java VMs were taking off as a research topic, and Jikes RVM was the first open source, really quality JVM. It was written in Java, and a lot of people got a kick out of it, and they also published solid research with it. So there's like more than 100 publications. Lots of people got their PhDs. And I really see that as an inspiration for doing the same thing in the WebAssembly space. So that's kind of why I started working on Wizard. And just to kind of state some of the things that you get from a research VM is that students don't know anything. I'm sorry. They start out and then they have to learn. So they need a thing to learn in. And so they can't learn in a big code base like V8. V8 is over 1 million lines of code. You physically don't have enough time to even read the lines of code in order to become productive. So you need a smaller artifact that's simpler. So that's one of the things that you get from building a thing specifically for research.
Okay, say what's your ideal size artifact?
It needs to be medium size. So Wizard is less than 40,000 lines of code. And probably the core of it is like maybe 12,000 lines of code. So it's like 2 orders of magnitude smaller than V8. Obviously, I still think that runtime research is fun. I think there's lots of new techniques, like new compiler stuff, new optimization. So like, obviously you want to have a base to do that with, but also WebAssembly is still evolving. We're adding features to it. Those features have to be implemented and experimented with. It's difficult to do that kind of experimentation in a production VM because they're typically not as flexible as they could be because they're tuned for performance. And so having a research artifact means that you could potentially implement things faster. And so you can steer the language evolution by doing experiments. And the other thing is that production VMs exist to be production VMs. And so they should be really tuned for that. And they don't need to be flexible for research. So Wizard is all about observability. And that's like what everything that we built is geared towards. And against V8 is about performance. And the other priorities are really far down the list. And then one of them is that the system actually is evolvable and that the people working on it can manage the complexity. So there's papers about Wizard. I won't talk about every one of them. We should start jumping into what it looks like inside. So one of the things is that Wizard has an interpreter. So most WASM engines prior to Wizard did not have interpreters. They were compile only. And so V8 in particular, the very first implementation only had an optimizing compiler. WebAssembly went straight into the optimizing compiler. You got machine code out. If you wanted to debug said machine code or debug the WebAssembly code, no luck. So instead, eventually you realize that having an interpreter is nice for being able to instrument. And also there's other performance characteristics that are nice about an interpreter, including that you don't have to do any work for code that's cold or never executed. So you don't have to spend time compiling it. So it turns out that WebAssembly is not easy to interpret because it's got structured control flow and it doesn't have just jumps. And so one of the things that I did, one of the first papers I published on Wizard is about the interpreter. And the takeaway is basically the WebAssembly code on the left, which has got like ifs and it's got blocks and things like that. You don't really know where to go. Like if you're an interpreter and you're running through the bytecodes, you don't really know where to go because it's implicit in an if that if it's false, you go to the else and you have to go find the else. So this little data structure called the side table is basically some pre-computed information that allows the interpreter to go to the right place when you have control flow. And so this allows you to run WebAssembly code without doing rewriting. And that's mostly important because you don't have to spend extra memory rewriting to a different representation to run it. But also when you do run the code, you're able to map back to what the original code was because you're in the original code. So instrumentation, you don't have to worry about, oh, it's this original bytecode offset maps to this machine instruction or to this other AST node or something like that. It also improves your startup time, so I won't go into the details about that, but basically it's faster. You don't have to touch the code except to validate it.
Could you just say
Yeah.
a little bit of it? Such a wonderful.
Okay.
Just explain what we see. Well,
This is a logarithmic axis of how much time does it take per byte to get going. So like 10, this is 10 nanoseconds per byte of code to get going. This is 100 nanoseconds, 1,000 nanoseconds. So to optimize a compiler, it takes roughly 1 microsecond per byte. So this is a scatter plot of a bunch of different programs. All the optimizing compilers takes a long time. Baseline compilers, which do less work, typically single pass, they're in this region. So they compile much faster. Interpreters that rewrite the code, they have to do almost as much work as a baseline compiler does, because they generate a new representation. This is the runtime. So this way it's bad, right? Slower. So obviously optimizing compiler, those are basically the fastest you can be, the lowest. Baseline compilers are a little bit higher. Rewriting interpreters, they're interpreter land. They're slow, order of magnitude slower. So Wizard is here because you don't have to do a lot of upfront processing. But it runs like interpreters. So that's what this graph means. Yeah. 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 So they would be there would be off this chart. Yeah.
That's really awesome.
Off the charts. Yeah. It's never zero. Okay. So obviously running in interpret mode is slow. If you saw the numbers there, it's like 40x slower than optimized code. That's not good. So you have to wait 40 times as long. So that's like just not good for interactivity. And if you're doing any performance work at all, like any optimization you do is swamped by a slow interpreter. So to even get reasonable performance, you have to have some kind of compiler. Wizard has a baseline compiler, and it's a single pass compiler that does not build in IR. So it basically generates machine code as you go as fast as you can. So the point is that this gets you in the range of being able to run things fast enough to be useful and also to give you transferable performance results. You make an optimization, you're like, okay, this is about what you would get in the baseline of a production engine. And this diagram is basically just showing like, this is a stack frame layout. The interpreter frames look a certain way. And in baseline compiled code, they basically line up. So you can switch between the interpreter and the baseline code by effectively just changing a couple of things. So if you're running in the interpreter, you do dynamic optimization, you generate machine code, you can just switch the frame over and run in optimized code. So that tiering up is like really simple. And also going the other direction, which is the tougher way, which is you're running compiled machine code, something has changed for whatever reason, you want to go back to the interpreter, for example, instrumentation, you can just swap a couple pointers and then jump back into the interpreter. So the frames line up, and that makes things really nice. Because I worked on V8 for like 7 years, and the de-optimization, where you go from optimized code back to the interpreter, just a bug farm. Just like so this is like pretty easy to see that it works correctly. All right. So you can get pretty decent code out of a baseline compiler. It all boils down to what can you figure out in a single pass through the code. So if you're running abstract interpretation, you can keep an abstract version of what the operand stack and the locals are. So you track what, for example, if you're allocating registers as you go along, what slot has what register. And you can also track constants. So you can do a few optimizations like constant folding or better instruction selection. And the whole point is that you generate code as fast as possible, but you make best use of the context that you can derive by just doing a single pass through the code. And so it seems counterintuitive, but you can actually get pretty far. So this program here is like got, 12 instructions. It's got a loop that looks kind of complicated, but carrying the register allocation up to the loop and through the loop, you can get down to like just a couple machine instructions. So it's like 6 machine instructions in there, which is, you could probably get rid of 1 or 2 of them, but that's about as good as you can get. So you can actually get decent code out of a baseline compiler. Okay, so you land there. That's the new point where you are. So you land solidly in the baseline compiler category. All right, so let's talk about dynamic analysis. We're going to talk about what's the point. So it's not too terribly slow, and it's got an interpreter in it. What do we use those 2 things for? And the answer is let's start analyzing programs, and that's where all of our tutorial actual meat is going to be. And the point is that interpreter gives us this nice mechanism to be able to say, that is an interesting point in the code. Why don't you call me every time that gets executed, and then I can do what I want in my dynamic analysis. So you imagine this execution point here, and you hit it, and the VM calls a user callback, and the user callback can do what it likes. And accessing the WASM program state can be done through a pinch point. We call it the frame state accessor, so we can see what's going on in memory. So in the program's memory, in the program's execution stack, and also the value stack. The way we implement that is basically, I'll skip over this one. The way we implement that is basically, why don't we just use an illegal bytecode? So that when the interpreter is running along and it hits a bytecode that's illegal, it marks it as a probe. So it knows that I was going to do a call or an i32.add. Instead, it's a probe. We call the user callback. Because we're running the original code, we make a copy. And so we have a copy of what the original code was, which means that we haven't lost any information. So if it was an i32.add, it was temporarily overwritten by a probe, but the original code tells us exactly what offset, what we should do. And it also means, so we can execute the logic that we should have executed, but it also means if we want to remove the probe, we can just copy the original bytecode over top of it, and it's just gone. And so the interpreter it goes back to full speed. So being able to remove instrumentation is actually super important because we can build things like code coverage. So for example, imagine that we wanted to know which of the basic blocks are executed. What we can do is we can just insert probes at the beginning of all the basic blocks. And then as they execute, they will just record the state. So as this probe executes, it flips this block, says this block was reached, and then removes itself. And as we continue executing the program, the next probe hits, records that it's executed, removes itself, and so on. So as the program executes, it's naturally removing the instrumentation. And then when we finally get to the point where we're tearing up the code, so we're compiling the code because it's hot, all the hot code naturally has already removed its probes. And so it will basically run at full speed. Probes are the one thing that you need in your VM to implement basically everything else. And if you can insert and remove them, then you can do lots of things that you can't do with static instrumentation. So these are an incomplete list of all the things that we built with probes. And basically everything that you're going to see today is built out of this one mechanism at the bottom. You can have race conditions on WASM memory. Yes.
So I can get a trace that I can use to analyze iterations.
Yep.
Ah,
Yep. So in the JIT, it's basically when you've inserted a probe somewhere, the JIT is basically going to insert a bunch of code to call your probe. And so that code might look like this because there's a couple of different runtime things that you need to bounce through. But we can improve that a bit. And so you don't have to understand what all machine code is here, but basically since the JIT knows exactly what probe is where, it can compile in direct calls to it. And for certain kinds of things like a counter, it may know that, oh, this is a counter. Let's just insert 2 instructions that do an increment. It doesn't have to go through all the rigmarole of actually going through the runtime. And so that means like big reduction in the amount of overhead. And so the JIT is basically just specialized to certain kinds of instrumentation. But I think what we're going to do is we're going to look at some of the code. I don't think we're going to actually do an interactive like development of a monitor, but we're going to look at what it looks like in the engine. Does that sound all right? Okay. We are going to have a look at. Okay, so now we're in actual source code of the engine. So just to be clear, when we write a probe and using this is like the lowest level mechanism. We're in the engine, we're compiling code into the engine. This code runs inside the engine. It's not inside the program. So we're not instrumenting the program. We're not changing the program state space. The program is still being emulated as before. This is running as if it were part of the VM. Okay, so the first thing here is this, yeah. This is Wizard. This is Wizard, yeah. All of WASM 3.0. No. Well, so Wizard actually can compile itself, can be compiled to WASM and run on the web page too, but that's probably not what you're. I hadn't thought of that. That's a good idea. We should talk more later about how we can hook Wizard up to things. I was semi-serious about compiling Wizard to WASM itself. I actually do that sometimes. So you run Wizard compiled to WASM code inside another WASM engine on a web page. Okay, so we're going to talk about this monitor. So this one is the memory stats monitor. And so this is some code that you can. Sure. Okay, so there's a thing in Wizard called the monitor registry, and we can just call this method. And so, by the way, this code runs when you compile the engine. So this all gets inlined into the engine, and so the binary has the actual monitor in it. So that registration thing happens at the compile time of the engine. So we register something called memstats. To implement a monitor in Wizard, you just extend this monitor class. It's got some various methods, one of which is on parse. So this method is called after the WASM engine loads a user program. And so it gives it the module, and it also allows you to say, oh, there's something wrong with this. That's what this error gen is. But what this one does is basically just instantiate this other class, the memstats instrumenter, run the instrumenter, and then at the end, it will report a few things. So this memstats instrumenter, it is a bytecode instrumenter. Maybe we should just show that. And so this is just a bytecode visitor. So the memstats instrumenter basically is just going to run through all the bytecodes in the program and look for certain ones. So the bytecode visitor is effectively the base class of everything that dispatches on bytecodes. So it's just a convenient way of using the visitor pattern to match over a bunch of things. You can also use pattern matching, but that's not the most important thing. So all of the WASM opcodes have such a visit method. So if we're interested in a particular opcode, we can just override that method in our class. So we can have a nice little compact thing. So our memstats instrumenter is basically exactly that. We're going to override the visit methods for each of the bytecodes that we're interested in. So I mentioned, if you remember, there's like 120 bytecodes to deal with memory. They all boil down to, most of them are either a load or a store. And so those all kind of turtle through these pinch points, the visit load and visit store. So we're not looking at specific load opcodes like I32 load. But what this one does is for all loads, we're told the opcode, we're also told the immediates and also the size. And we've got some data structure, which is over here. And we're going to basically create one of these two probes depending on this variable. It's not that important, but 32 or 64-bit case. We're going to create one of these probes, and then insert the probe here. And so this is just a helper method in the bytecode instrumenter, which just inserts the probe right where we are currently. Similarly for store, there's going to be something where you basically insert a store probe. And so this load probe is going to be defined below, which is here. It's just an instance of this class, which extends one of these other probe classes, and it has a fire method. And all the fire method does is it calls into some record in our data structures, excuse me, which is below, and gets the address. So both load probe 32 and load probe are that. And store probe is very similar. And we'll talk about, we can talk about the guts of that in a minute. But basically all it is we're just inserting some instances of these probe classes at various things, at various locations. Okay, so if you saw above, there was more than just load and store. There's also memory grow, there's memory init, there's memory copy, and memory fill. All those have to do with memory. Maybe you want some stats on those. Okay, so a good example of what one of these does, which is sort of non-trivial. Let's look at the copy probe. So this is going to be inserted every memory copy instruction. And basically what it does is this fire method gets this thing called a dynamic location. This is basically going to be a representation of the runtime context of when that instruction is executed in the program. So I'm pretty sure that one is in. So this is basically coming from the base level method that we're overriding. The dynamic location comes in here. And if we look at it, what this does is the dynamic location has got a frame. So we can look at the current frame that's executing, and the frame has something called a frame accessor, and that is the thing that gives us access to all of the WASM state. So if we look at that, that one is at over here. It's got a bunch of methods that allow you to access all the things that you'd want to know about a frame. What function we're running, what's the program counter of that function, like where are we in the code? Is the frame unwound? Because it's possible that you could get a frame accessor, hold on to it, return to the program, and the program runs and that frame goes away. So we can actually check that that's happened. So because this is a actual just thing in the engine, that's possible that we could write instrumentation like that. We can ask, what's the depth on the call stack? Like, so how many frames are there on the call stack? And we can also ask for the caller. So you can do a stack walk. We can ask for various things like how many locals are on the frame, how many frame, we can get the number of operands. So how many things are on the operand stack, and then we can get all the values too. So we can get all the values of the locals. We can get all the values of the operands. And, another thing that we can do is we can even change the frame too. So there's an additional thing that if you request that, the frame writer allows us to change the locals. So we could go in and change the value of a local variable. We can change the value of the top of the operand stack. We can push onto the operand stack. And there's various other things. We can even change the control flow of the stack too, control flow of the program. Obviously that's dangerous because we could break the program. We're now changing the program's behavior on purpose. So the engine has some checks that you're not breaking the type system of WASM. So for example, if you overwrite a local variable, it will at least check that you have a value of the right type. So you can't change like an I32 local to be like a reference or vice versa. So it will catch some things, not everything. It's not possible to catch everything. But the basic idea is that it gives you the unnatural powers of a monitor to change the program's behavior. Okay, does that kind of make sense? So you basically get this frame accessor thing. You can ask for everything that you want, and then you can look at, all the program state from the function. So I mentioned the function. From the function, you can get to the instance, and the instance has like the memories and the tables and the exported functions and things like that. So you can transitively get to the entire state of the program. Okay, and if we run this thing, I think we do, the way we do this is, oh man, now I can't see that. Yeah. Use memstats. And if we run it on a benchmark like big G. So what this one does is that if you remember, it basically was visiting all loads and stores in the program and just keeping track of how many reads or writes happened to each. And so it did that for also all the copies and the fills and stuff like that. It's actually the bulk of the program, other than the instrumentation, was making this really nice colored printout. If we look at the help, there's a bunch of monitors. So in that monitor registry, everything that had a name will also have a little help blurb. And so you can see the things that have been built into the engine. So like the blocks monitor basically just counts basic blocks. I mean, they all describe what they do. The branches monitor basically counts every direction of every branch. You can get calls, you can get a call graph, you can get the profiler. All of these things are actually built in using the probes. And they're all written using the same kind of engine interface. So they're all kind of manually going through every function, looking for the bytecodes that they want, inserting the probes, and then managing data structures behind the scene. And if we look at the actual number of lines of code in this one, it's like 200 lines of code. And, you know, a good chunk of that, some formatting and messing with the actual data structure here. So I spent some time actually optimizing this to be really efficient. But this is like, it's a bit low level. So I think we're going to hand it off to Elizabeth, who's going to talk about how we make this a little bit less manual. But before we do that, Ava, any questions about what's going on here? Yeah. So yes, so for my course that I teach on virtual machines, project 2, all the students in the class have to write wizard monitors. I point them at the documentation for the engine and for the language. And basically it's a question, can they accomplish that? A lot of students are able to do the project in one day. Some took more. The feedback has been pretty good, and we've improved some of the APIs based on that. But this is something like, these are undergrads, like, you know, like 3rd and 4th year students taking this course, and they're able to do it. Nobody has told me that they've written a monitor from scratch. Yeah, there a lot of the functionality is covered. Like if you see what's going on here, I try to make it batteries included in the sense there's lots of things you can do. There's like a profiler and all of these things. And we keep coming up with new ideas and putting them in. And I feel like we're now getting to the area where making those programmable things is more going to move towards what she's doing.
You should show the coverage or the control model.
Oh yeah, you want to? Oh yeah, this one might take.
I've used this a bunch in trying to figure out what's going on in the program.
Let's do. Okay, so this one is basically just like a branch monitor. It counts the direction of every branch and also loops. And then it gives you this nice printout of the bytecode. And so this one I spent many hours tweaking the ASCII art. So I'm inordinately proud of this one. But it basically will show you for every branch which direction it went, how many times, and it will like make those nice little arrows. So all the branches that go forward, they'll have the arrows on the left. And so they go back around, and all the branches that go backwards, they have their arrows on the right. And so for every loop, you can also see like it going back around again. So it kind of gets out of control for real programs because they get enormous. Like, so if I run this one, it's going to be kind of probably going to be a nightmare. Actually, not too bad. This one is pretty. Yeah. You can see there's some nested loops. Yeah, this is like a 1,000 bytecode function, so it's still kind of manageable. Why is which useful?
Why is this tool useful? Because of WASM, you just have loops and keys. You don't have random basic values. Why do you need so much?
Oh, this one I found this very useful to understand where's a program going. So usually when I'm debugging something like because for example, you have a BR that says depth equals 1. And so where that goes to is the end of whatever is at depth 1. And so that you can just like literally just follow it now to where it lands. Oh, it's there. So this would actually be very nice to have in a like a GUI, like if there was a VS Code thing that we could load to, you could like click around, it'd be very useful. Okay, other questions? I think we're ready to start in with the WAM.
Cool. All right, so has been said, oh, I'm gonna unmute myself. So as been said, we're trying to make this less tedious to build out through having, oh,
Plug in.
you're right. Through having some higher level abstraction for building out instrumentation for WebAssembly. So that's where WAM comes in. There we go. Okay. Can you see that in the Zoom? Yes, you can. So we're gonna talk about WAM today, which is a pretty great framework for building out instrumentation. We're trying to do this to reduce ecosystem fragmentation in the WebAssembly ecosystem, because there are some interesting properties about WebAssembly that make this pretty powerful if we accomplish what we're trying to seek out to accomplish. So for one, WebAssembly is a polyglot, and two, it's a managed language that runs on top of a virtual machine. And since it's a polyglot, you can have all of these different languages that are working together to ultimately like provide some functionality as an application. So theoretically, you could build out language agnostic tooling because you're targeting their targets. So if you have one tool to be able to instrument across languages. Also, since WASM is a managed language, you could theoretically create tooling that's portable across machines. So you don't have to build stuff for a specific machine architecture. You build it for the virtual machine and it works. And then since it's a virtual machine, the engine itself can manage instrumentation. And this is really helpful if you're thinking about like dynamic instrumentation. So what Ben said about removing probes as they execute in a coverage monitor. You can't do that in traditional like source level or bytecode level instrumentation because it just always exists there for all time. But for an engine can remove and de-optimize code if you've JITted to remove that instrumentation for you. You can also dynamically insert instrumentation. So if you're thinking about having a production engine being able to dynamically turn on a monitor, you can debug or get some observability on some weird behavior that's happening in production. And then once you've collected the information you need, you turn it off and it's as if it wasn't there to begin with. So some really powerful ideas here to make instrumentation really great for the ecosystem.
I can try to combine some commands that I use something generated by or it doesn't work.
For which part? Which one? I didn't hear the beginning of the polyglot. Yeah, I think that it's moving more toward that in the context of like having like WIT interfacing between WASM components. So you have this defined barrier of types that each language can actually talk about with each other. So yeah, I think there's kind of like some fuzziness around that, but I think that it's getting more accomplished with WIT. Ben may know more about like the module side of it, but
Yeah, I mean, interfacing different languages, you have API problems.
yeah, which is what WIT is trying to do.
Yeah.
Mhm.
Yeah. Yeah.
Yeah, for sure.
Sorry.
There's always problems, but We're trying to make it better, at least from like this instrumentation standpoint. Yeah, so high level idea of the architecture, you have some program that you want to instrument with some tool. So your tool is expressed in the DSL, which is kind of this entry point for the framework. It's AOP style, so you can say where I want to inject based off of some events that you've exposed to the DSL. So this is the tool.mm script. And to keep from scope creep in the DSL, we offload some more complex tooling logic to any language that can compile to WebAssembly. So you compile the WebAssembly to the language to WebAssembly, and now you can provide this functionality as a library to the tool itself. So now the tool can use this WASM module to do arbitrary logic in the probe, which you would have to, in the tool, you pass the application state down to the library. Yeah, then you have the compiler, which has two different backend targets. You can either target the engine interface, and this is, we called it WAI, so WAM engine interface, and yeah, and what this looks like is it generates this kind of program agnostic representation of the tool. So you notice that the program itself is not an input to the compiler here, and that's because it isn't specific to the application. It really just encodes metadata inside just normal WebAssembly code, and it requests specific things to happen from the engine. So it'll tell the engine where you want to instrument and what you want to insert, and the logic you want to insert is just WebAssembly code. So it just encodes these probes as WASM functions that get run at runtime based off of the matched locations in the application. So it's program agnostic. It just has basically instructions to the engine for what to do. Then at runtime, so now you have an actual application to bind your instrumentation to. So the engine will look for these probes that have been exposed to the engine by the tool.wasm file, just as exported functions. And these get matched to probe locations in the application. And then when you run, it'll do these probe callbacks for you. So for observability, you can observe anything the engine can. So bytecode level events, engine level events, considering like GC operations that happen in the engine, you can instrument any of this. For performance, there are some new optimizations that we've built into the Wizard engine with our implementation of WAI. And I'm going to talk about what those look like for the JIT, baseline JIT and the interpreter in a bit. For intrusiveness, there's not any risk here since the monitoring runs in a different state space. Yeah, and for portability, you have the same monitor. So this is a program agnostic monitor. It runs across any program and it can run across any engine that implements WAI. The only engine that does that right now is Wizard, but we've been talking with other engine implementers to figure out what it would look like to standardize this interface. So for now, we have this bytecode rewriting fallback. So you have two different targets in the engine, this WAI target, and then a bytecode rewriting target to allow the same monitor to run across any engine because it's just going to be WASM code. So this is this bytecode rewriting target that lets you run across any engine as a fallback. So here you have to have the application as an input to the compiler because it's rewriting your program bytecode. So the output on the right-hand side is this now instrumented variation of your application. So it's just your app.wasm plus the tooling code represented by these like little red blobs. Yeah.
One question. I would like to add the extension. This is a GC extension. For instance, imagine that I would like to add a loop back, kind of references.
Yes. I haven't added that capability in the DSL, but you would be able to do that, yeah. If you're just adding a new like GC type, then it would just add a new type to the WASM module, yeah. The engine would have to do that. I mean, the tool eventually, like if I add that capability to the DSL, which it doesn't have that capability right now, then there would need to be some type of like check in the DSL to make sure that you're not like breaking WASM type checking. But if you then try to run this and something was wrong with the type that you generated, the engine itself would have to validate that as well. Yeah. Yeah, so this is just you're instrumenting WASM code with WASM code, so it runs across any engine. So you can just run that with any new library dependencies that you have added because of your tool. So observability here, you have a little less observability than before because now you can't observe engine level events. You can only observe that which runs on top of the engine. Performance, it's also very fast because you just inline your bytecode into your application bytecode. There is some intrusiveness risk here. So as an example, if your instrumentation reaches an unreachable bytecode, then it's going to trap, which it's not able to handle in your bytecode. But if you had handled this in the engine, or if you'd done engine instrumentation, your engine wouldn't make that. It could handle the trapping instrumentation and not impact your application actually running. So there is some risk here for changing the behavior of your program. And as for portability, it runs anywhere because you're just running more WASM code in your WASM code.
Now, adding new byte. So that at some point, it's like think of byte like that.
What do you mean?
Adding new
I
bytecode.
would like to add a new bytecode, experiment bytecode on that.
Wave's not really,
The instruction that they have in mind.
yeah, you'd have to start editing the engine.
Yeah.
You have to make edits to the engine to support that.
Yeah, the engine, it can't, you would have to write valid WASM from the engine standpoint.
For an experiment, I'd like to try something new. Totally not designed.
Not for that.
Mm-mm. No, like this is just,
This for that.
yeah, you would have to modify the engine so that it knows how to execute that new bytecode.
I could imagine that if you intercept the trust saying that this instruction is not valid, that there is something else, or you can see that.
That would be like a new capability that would have to be supported by the engine though. Yeah, so if we expose that to the engine interface, maybe, but we would have to expose that like capability to it.
Extension. I would say you don't
It's not that common that the DSL maybe needs to have a mechanism for that, but people have done that. So Elliot Moss added a whole transactional extension to WASM and Wizard. It's like pretty involved. I think if it's like a one-off bytecode, maybe it's not that high demanding feature.
Mhm.
It implies a lot of tooling too, like all the things that print out the bytecode now have to know about it. So like WASM object dump and WASM tool print and like all those things.
Mhm. Yeah.
Getting into a pretty narrow use case.
Yeah, so high level WAM, you write your instrumentation once, it takes care of the injection strategy, and it promotes a lot of portability for your application use case or domain. So let's look at what the engine interface looks like at a high level. Let's say you have some program that you want to instrument, and then you want to instrument it with this monitor.wasm file. So you have this exported function, which is your probe callback, and it encodes, this monitor.wasm encodes some metadata basically into the WASM module that instructs the engine on what you want to match to insert this probe callback and what you need from your application, like the state, to execute this probe callback function. So if you remember Ben showing this frame accessor thing that has access to the actual in execution frame, So that is where this arg0 would come from. But instead of having to create this really expensive frame accessor, you can just request the state that you want. So in this case, it wants the immediate 0, which is the target of the call. So this is literally the immediate on the static application bytecode. And then arg0 is the top of stack. So it's the first argument to this call operand, opcode. So it looks like it matched on all the calls and inserted these probes. And when it dynamically reaches this point in the application, it will call down on the WASM engine with a runtime call. And then the WASM engine will bundle the arguments that it wants, the immediate 0 and arg0, pass it to the probe callback. That will execute and then continue on with execution and continue. And what makes it fast, you'll observe that we're requesting the subset of application state that we want for our probe to be able to compute what it needs. And this just really boils down to this static constant. So it's the immediate on your call opcode and a stack location. So the location on the stack that you're wanting to get and pass it to your probe callback. And so since we have this subset of state, it can be optimized with intrinsics and our different tiers of the engine. So it can recognize that there's a probe here. This is the state that I want to pass to it. And now I can optimize how I actually pass and invoke that probe. Another thing is that the monitor is just WASM code. So you use your normal tiers to execute this code. It looked like you had a question. Okay. Yeah, it's just WASM code in that like you're instrumenting WASM code with WASM code. So you would still have to have capabilities in your engine to handle that instrumentation. But at the end, like you can use your normal optimizations, like how you do WASM inlining, to then. I don't think I understand your question. What's your?
This is relevant.
Oh, yeah. You mean like the different targets?
Yeah.
So this is for the engine target specifically. For the bytecode rewriting target, it's like this isn't how it works in the bytecode rewriting target. Because the engine doesn't know about the instrumentation. Let's say that this was bytecode rewriting. This call, the instrumentation on this call would not call into the WASM engine. Rather, they would be doing like these WASM to WASM calls where the state is bundled inside this like app plus tool.wasm, and then it can call into like libraries that are happening. But all of that kind of gets inlined in the bytecode rewriting case. This is just for the engine interface. Yeah, so since it's just WASM code, you can use optimizations like inlining, and it's just doing the normal optimization in your JIT with some awareness of this being a probe. So it still has to bundle things and invoke your probe. Yeah, so runtime calls, they're super expensive. So how can we remove some of these runtime calls and runtime calls in that it's calling down into the runtime? We want to remove these to make things run a lot faster. So what this looks like in the interpreter is doing this trampoline optimization where you generate these little machine code stubs that can be used to invoke my probe callback more efficiently. So when I hit some probed location, I have some transfer logic, which does my bundling, switching WASM contexts, and then invoking the probe itself with these like bundled pieces of data that I requested. And then it can continue on back into the application. So now I don't have this expensive runtime call anymore. Instead, I have these little machine code stubs that are running to optimize this call. And then in the baseline JIT, we have this WASM to WASM optimization. So I have this little machine code stub that's now inlined right at the location of the probe. So I'm going to do my transferring, invocation, and continuation all inside here. And it just does this normal WASM to WASM operation inside the JITted machine code. And there's no expensive runtime call here. And then you can do a further optimization to inline your probe logic. So now you don't have any calls at all. It's just all the straight line code. So I'm not going to dig into the performance of this. I'm going to talk more about that on Thursday during a presentation. If you're interested, like attend the presentation. But yeah, just know like this can be very, very fast, and that's awesome. So from the standpoint of the entry point to this framework where you write your stuff in the DSL, this is what it would look like. So here's an example monitor. It looks very similar to dtrace if you're familiar with dtrace. So at a high level, we have some global state that we're using. We're accruing something occurring over time in our dynamic run of the application. This is where I'm wanting to match. So I specifically want to instrument all of the BRIF opcodes and WASM when I want to insert. So I want to insert my probe right before the BRIF. So this would be more relevant for the bytecode rewriting target than the engine, but beside the point. So I want to insert before. And then we have some further constraints. So let's say I want to constraint on, I only want to insert my probe if my BRIF is at location PC of 25. So this is the byte offset within some function. If I see at PC offset 25 a BRIF, then I want to insert this probe. And then here's just the probe body. Does anyone have an idea of what this is doing? So I'm accruing some count over time. I'm checking if the top of stack is 0 or 1 or non-zero. And then I increment this location with this result. It's checking whether or not the BRIF was taken at this location. So if it was taken, then I increment. If it wasn't taken, or I still increment. So it's 0 and 1. Yeah, this was just to give an example of the predicate. This isn't really important, but at a high level, it's checking like what branch was taken for your BRIF at the location that I instrumented. Yep, you can. Yeah, you could also like predicate this on arg0 or anything really. I don't think I do in this talk, but I can show you an example later if you want to. There's also some nice, we're gonna like run, it's gonna be too long again, but that's okay. So there are also some nice language features like glob matching. So if you're wanting to match on multiple different events, you can use normal globs to do that. So this is going to match on all of the WASM opcodes, all of the load and store opcodes specifically. So this is going to instrument all of the load and store WASM opcodes. It also has powerful storage classes. So there are things called bound functions and variables. So you'll notice that this data size is not declared anywhere in here. It just shows up and you can use it. And that's because this is provided by the load or store events. So when you use things like bound function and variables, you need to make sure that the thing that you're instrumented actually provides that bound variable, or it's going to not be defined. So this data size is the size of the data that this load or store operation performs. So if you're doing an I32 load, then that's going to be loading 4 bytes from memory. So the data size would be 4 and so on and so forth. And there are a ton of different load and stores in WASM that can be done on a lot of different data sizes. So this kind of like keeps you from having to write the same probe over and over and over again with these different data sizes. There are also derived variables, and this is variables that are, you use other bound variables to basically derive the value of them. So the effective address in WASM load and store semantics, you have a static and a dynamic offset. For like the static part is just an immediate on the opcode. The dynamic part is from the stack. So this effective address then just does this addition for you. So you're not having to rewrite like static offset first plus dynamic offset every time. You just use the effective address and it does that computation for you. Then you have probe local state. So these unshared variables, every probe gets its own instance of it. So at every load and store location in my program that I have a probe at, it has its own instance of these unshared variables hit and miss. So there's another type called shared, and this is where they all have access to the exact same variables. This one lets you accrue state per location. This one lets you accrue state per event. All right, then you can use these WASM modules, like I said before, to do arbitrary complex probe logic. So this is using some WASM module called cache that it's going to call some function called check on. So this is just some exported function that's provided by this WASM module. Does anyone want to guess what this script does? So we're using some WASM library called cache. We're instrumenting all the load and store opcodes. We have an instance of hit and miss per probe location. I'm calling this check function, passing the address and data size. It's implementing a cache simulator. Yeah. So I'm checking whether or not if I did a lookup on this cache implementation, if I would have had hits or misses and what those would be and incrementing the values. So another thing is this report tag. It says the state that's on that winds up. Okay. At the end of program execution, I'm going to flush the value of these hits and misses of all the instances of them. So I can see at the end, I had this many hits and misses with this implementation of my cache. And you can swap out the implementation of your cache. You keep the same monitor definition, swap the implementation, and you can see how well or not well your cache implementation does for this program. That makes sense? Cool. Does anyone have an idea of what this one does? So we have a map U32 to U32, and it's going to be reported at the end, and I increment based off of some bound variable called category ID when it's hit. Matches on all opcodes. Yep. Yeah. So if you're thinking about like the categories that Ben showed on the one slide with like all the groupings, it can tell you this high level profile of how heavy like some specific category was. So if you're wanting to see if it was a lot of float operations, then this would help you do that. Yeah. So again, we don't have a ton of time for like showing this live demo. But if you're interested in like doing this offline or like take a look, there's a repo that has a bunch of different example monitors that we can run through. And it has binaries that will help you like run on your machine. So you're not having to like set up a bunch of stuff to get this going. So if you want to take a look at this. And I can show you. I'm just going to show you what this would look like. Where is share? All right, at a high level in this repo, we have these folders. So inside apps, you have example WASM applications that you can run on. Probably the fastest one to run is branches.wasm because I just hand wrote that one. To give an example, the other ones, if you're running on a Mac, it's going to be super slow to run because you have Wizard compiled to the JVM, and then your WASM code is interpreted on top of Wizard. So it's going to be really slow to run. So like you might want to try to run this on very small applications if you're running on Wizard. And then in binary or in bin, we have the binaries that you can run that have been pre-compiled for different machines. So WAM we have for Mac x86 and x86-64, and then Whizzing we have JVM. You run that on a Mac x86, 64, and x86. So yeah, and the libs directory has all of the libraries that would be relevant for the monitors that we're going to write. And then we have a bunch of example monitors inside this monitors directory. The only one that's been filled out is this branches one, which is the example. I think I might take some time tonight to just write the actual answers to all of these and put them on a different branch in case people are interested in like playing around with this and trying to figure out what they should be. But for now, they're all just empty and they have they just say like where to write your code and what at a high level this monitor does. So I can give like a quick example of what this branches monitor does, and it does branch profiling. So this will help you see like what branches were taken during program execution and how often they were. So it helps you find the hot branches basically in your code, and you can do like restructuring your code to optimize based off of that profile. So at a high level, we have a WASM match or a probe match on this location. And there's some really nice, there's this nice command line option that I've made to make it like more intuitive to figure out what variables are bound by matching on this event. So if we rerun that, so I'm running the command line tool for WAM. I'm using the info command and I'm passing in this rule specifically. So I'm wanting to see what would be matched and bound by using this match rule, which I use inside here. And when I do that, it prints out what's been matched based off of this glob. So WASM obviously is going to match the WASM provider. There are a bunch of bound variables on this that can be relevant to use in your instrumentation code. Opcode, similar thing. And then star if is a glob that's going to match on any glob, like any event that matches that glob. So if and brif specifically, these are the bound variables for those events. So you can see that arg0 is used inside this monitor, and it's bound by both the if and the brif event. So that means if I use this, I'm able to use the arg0 bound variable inside my probe body. So if we run this, it's going to... All right, so if I run... Whoa. Why is it doing that? Anyways, if I run this command, it's using the WAM command line interface. We have the instrument command, and I'm passing the script that I'm wanting to instrument and telling the tool like what I want to instrument. So this is going to be using bytecode rewriting. So if I run this, it's going to... Is it not? Okay, it didn't work at first. Let me rerun that. Okay, so it writes to this output.wasm in my current directory. And if I print this, now I have this human readable WAT representation. So if I look at this, it's all of the original application code plus my instrumentation code. So if I look at the original, like branches.wat, it's like this many lines, 125. The output.wat is many more lines. It's like 500 something lines because it's doing a bunch of extra stuff just in my original application code. So it's the application code plus my instrumentation code. And if I run it, then it's going to run my original application, but also flush the results of this instrumentation because of these report variables. So I'm running this on top of Wizard. This is using bytecode rewriting. And I have a library that's now a dependency of output.wasm, and it goes and it flushes all of this state. So if you read through this, you can see these taken total, taken branches. So all of these are the report variables that were inside here, and it's flushing the state for all of the places that were instrumented. I've reached 1230, but I can show you really quick. Feel free to leave if you want to, but I can show you what the wizard target looks like. So now I have my output.wat, which this is using way, so it's against the engine target. So it's that standalone monitor that is not specific to the application itself. It has a bunch of exported functions, and this is where the magic sauce is. So this has the, it basically documents the function that is a probe callback, and it instructs Wizard on what to do. So you'll notice that the WASM opcode star if has now compiled down to all of the matches for it. And this so this allocates, okay, this is function 70. Function 70 takes 2 arguments, and you can tell this because of these braces. So this is syntax inside the export names for like the 2 arguments that I have in my function. This is what I want you to pass to me. So this 69 is another exported function that is going to allocate all of my state for a probe. This is the information I need you to pass me to do my allocation as I need to. And then when you run me, you need to pass the results of this call and arg0, so top of stack. At a high level, request data being sent to me from the engine. We can dig into this more if you're interested. But it encodes this high level data to the engine on what you need to match and what you need to pass me when you call me. And then when I run it, we're going to run it on Wizard. We need the multi-memory extension. I might have compiled it before you did that. And now I think I did this before. Hold on. Yes. So now I'm gonna use my way to say I want this monitor to run on my program as you execute me, telling the engine to do it. This is the program, and this is the libraries that it depends on, and then this is the target program to instrument. And when I run it, it also does the same thing. So it instruments, but this is against the engine interface, and it's flushing all of my state at the end. So that's like high level overview of the framework. If you want to see more, feel free to come to my talk on Thursday or like talk to me later. But yeah. Thanks for listening, guys. Yeah.
It's lunchtime, right?
I guess so.